So hello, everyone. Welcome to the US-RSE 2023 conference tutorial, Introduction to Spatial Data Processing. Today, we are very happy to have Nick Santos here to give this tutorial. First, I'd like to remind everyone that we do have a code of conduct that we ask everyone to follow, and pasting the link here in the chat. And if you are not yet a member of US-RSE and would like to become one, you can join on the US-RSE webpage right here. Now, this is a hands-on follow-along tutorial. I'll be acting as moderator and keeping an eye on the chat for questions in case you get stuck. But since we generally have a lot of people in here, help is offered on a best effort basis, meaning the instructors won't necessarily be able to spend a lot of time with an individual person or stop the tutorial. The tutorial is being recorded, so you can follow along at your own pace once it's released. As a reminder, the material for the tutorial is available in the Google Drive, and I believe pretty much what's in the Google Drive is this link here, so I can paste that link for Nick. And with that, I'll introduce Nick. Nick Santos is a programmer, GIS specialist, instructor, web developer, and environmentalist. Nick works at the Center of Information Technology and Research in the Interest of Society at the University of California, Merced, where he develops models, software, databases, and applications to analyze and understand environmental impacts and indicators. Nick also teaches GIS and is the instructor for Coursera's 5 course specializations in GIS, and is an administrator of the Spatial community, an open Slack community for spatial professionals of all types to solve problems, share knowledge, and socialize. With that, go ahead, Nick.
Great. Well, thanks, Lauren. I appreciate you organizing this workshop, and to everyone that put work into the conference. I'm really glad this community is coming together. And yeah, so we'll take it a little slow at the beginning. Lauren already introduced me. You have a sense of my background and why I'm here talking to you at all. And just to kick it off, I'm going to give a quick overview of approximately what I expect the schedule to be. I feel like, especially with remote tutorials, the number one question I often get is, so what time do you expect the break will be? So we'll just take a quick look at the schedule here, and not my email, the schedule, which is here. So if you already opened the link that Lauren sent, you'll see a schedule, and it is it's different than this one, which so I just updated this to what I expect is actually in here. It's the same content that was in the initial description of the workshop. It's just been rearranged a bit based upon how the material came together for the workshop. So we'll do the welcome here, getting everybody in. I'll try to get to know you all a little bit, and then we'll make sure everyone's set up and ready to run the code. And then we'll learn a bit about simple mapping, an introduction to spatial data types. We'll go into spatial joins and aggregations and doing a bit of mapping. And then we'll take a break, my guess, about 2 hours into the workshop. So Pacific time, that's about noon, and 1 o'clock Mountain, 2 o'clock Central, 3 o'clock Eastern. And then after the break, I find it's important to get into coordinate systems after the break because it usually makes people's eyes gloss over a little bit, but I think maybe you all will be a little different than the groups that I'm used to teaching. And then we'll get into working with raster or image data and doing zonal statistics, which is sort of a way of joining that back to other types of data. And then we'll wrap up and get into some further resources. And before I dive in further, this is all new material for this group because I'm frequently teaching spatial information to people who have zero computer science background or very little computer science background. And you all, as a highly educated and highly practiced in computer science group, are pretty different because most of what spatial data is just an add-on to computer science. And so we can skip a lot of the things we have to go over with other introductory groups and dive right into the parts that are interesting. And you naturally won't be able to do everything after this workshop, but you should have a sense for the core concepts that you need to know that will let you all do what you do in learning the parts that are specific to your domain or expertise after the workshop. So that's my goal. Any questions before I go any further? Let's see. Okay, well, I'll try to leave space when I ask if there are questions. I know it takes time to get unmuted, but if I move on too quickly, feel free to drop it in the chat or just get on mic and interrupt me. I'm totally okay with that. And as more people are trickling in, what I like to start off with is tool that you've probably experienced in some form or another called Poll Everywhere, and where I ask you some questions, and it is not showing me. Oh, here we go. So first thing I like to do is just get to know where you all are here. So if you go to pollev.com/nicksantos507 in your web browser, you will be able to respond to a few questions I have just to get to know you all as a group. So we'll give time for you all to open that up, and then we'll go through a few questions before we jump into the rest of the tutorial. And thanks for putting that in the chat, Lauren.
Happy to do so.
Oh, and no, it's not super clear on this map, but if you're out in Alaska or Hawaii, you're considered west by the US Census Bureau. Okay, yeah, mostly Midwest and Northeast. I can't fill out the poll, but I'm out west, so add one to that. Okay, that should be most of you. I'll give this about 15 more seconds. If you missed this one, it's okay. This is just a getting to know who's on the call type question, but after this is where we actually talk a little about our experience. So, okay. Okay, moving on to the next question. Knowing that you're a group of research software engineers, but also that means all kinds of things and all kinds of experience, I'd like to know what your Python experience is. You don't need to be a Python expert for this because I'm hoping that the code is pretty readable, even if you've done very little work in Python, but I also kind of expected this type of result where a lot of you have a fair amount of experience in Python. Some of you will probably be looking at my code cross-eyed being like, why did he do that? So, and that's okay. Okay, and I know a few people are still joining. We'll give this question a little bit longer. This is great. Comfortable reading code or writing basic scripts. If you're at either of these levels, my hope is all the code will run as is that we're going to use, but my hope is that there's some space for you to practice and tinker with it, but that you don't necessarily need to be a Python expert to tinker and test out some different stuff. The workshop is using Python as the example, but really trying to teach the spatial concepts generally that you could apply to whatever language, framework, application, whatever it is you want to use spatial information in. The concepts we're going to learn today will apply elsewhere. Okay, I'll give this one. Looks like we got about 10 of you probably responding to this one as well. Give this one just a moment longer. Okay. Great. And then I would also like to know what your experience with Jupyter notebooks, and there's a site, mybinder.org, but binders generally. If you don't know what it is, you could say I've never used Jupyter Notebook, but yeah, I expected that a lot of you probably would have plenty of experience in this as well. That's what we're going to use today. They're very conceptually simple to get used to if you haven't used them. And if you haven't used Binder, it's a handy sort of wrapper that lets us launch a Jupyter Notebook in the cloud for free. So I think it's a really nice tool for a workshop like this because you all have to do zero setup in order to get running code. Okay, I'll give this one a moment longer for anyone else who wants to fill it out. Okay, great. So yeah, for anyone who's never used the Jupyter Notebook, I'll give a quick note on using it as we get into it here too. And then last question I have for you to start off is, what's your experience with spatial data or GIS? So whether you have no training and no experience with it, and that's why you're here, or you've received some spatial data and you know how to load it up in some way to look at it, or you took a class at some point, but you've forgotten it, or you're comfortable with it in some form, like a graphical interface, but you want to see how to do it in Python, or you're very comfortable with it, then all experience levels welcome here. We're gonna assume no training and no experience, but I think that there's something for everybody here. I think my hope is that you'll have something that you could take away. And that's awesome. I'll note, like in a lot of those courses I was saying, I teach to people who have basically no computer science experience. There are a lot of people in this category C, people, especially in the environmental sciences, who took a class when they were in school at some point and then didn't apply it for 5 years, 10 years, and are like, I need to learn this again before I touch it. So it's interesting to see the totally different distribution here. Okay. And yeah, question or note in the chat is someone who's used Google Colab if it's similar, and it is very similar to Google Colab. Or Binder from the previous question I asked. Okay, so let's leave these here for now, and just pause one more time. Any questions, any thoughts, anything anyone wants to discuss, ask before we get started? Okay, great. I haven't given you anything too technical yet. So here's the link. I'm going to put it back in the chat again for anyone who came in late. That link is all of the resources for this tutorial. So if you go there, there's just a GitHub repository. It's completely open. You don't need to be signed in or anything. You can use it in the future. And there's a README here that describes stuff you already know being in this workshop, but I'm trying to make this notebook also accessible to people after the tutorial's over when it's not instructor led. But what you need to know is all you need to do is click this launch binder button at the bottom here. And if you do, it'll make your page look like this. And it should load pretty quickly. Whenever I change anything about the dependencies, it takes it about an hour to rebuild the containers that they use here. But as long as it's been loaded recently and I don't change dependencies, it loads up pretty quickly. This is a free service, mybinder.org. You can get set up. You just put your GitHub repository that has a Jupyter notebook in it, and it'll do the rest of the configuration for you. If you need dependencies, you can provide an environment file for Conda, and it'll build a Conda environment for you. So that's pretty cool. For those of you with minimal Python experience, just know it'll set up the whole Python environment with all the dependencies, and that's all you need. And so it booted me into this, which is what we were just looking at. Note that the only part I've changed on my computer is this. The schedule in your notebook is different than what I showed before. But everything else is the same. I wanted to change some things, but I didn't want to rebuild the containers. So we're going to go with it. But I want to point out just a few things about this interface as we get started. It's a little better actually than the Jupyter Notebook interface I was running on my computer. It gives you scrollable data tables, which is pretty nice. You have a file browser over here, which mostly you won't need, but towards the end you may want to explore a few things that we output in the data folder. So here's your file browser. You could see some other information about what's running over here. And you can get an outline of the whole notebook here. So since I've used headings throughout it, if you want to quickly move up and down the notebook at any point, if you are at the bottom, but you want to come up and reference something, you have the outline here. Also, for one thing I'll note about Binder is it times out your kernel, your Python, your actual like running Python environment every 10 minutes if your browser tab's idle. So if you're switching back and forth between watching what I'm doing and actually running it on your computer, just make sure you kind of check in occasionally with your browser tab, because if you don't, you'll get, oh, this one didn't. Oh yeah, it did. It says no kernel over here, but usually it'll give you a pop-up like kernel died unexpectedly. If that happens, all you need to do is click OK, and then you just run some code again, but you have to run the code starting at the top. Let's say it happened down here. I can click into the cell here, we call them cells, and just do run. There's a run all above selected cell. So that'll catch you back up. If the kernel dies and you want to get back to where you're trying to work, run all above selected cell will get you caught up. There are a few operations that are pretty fast. This whole notebook will run in like under a minute on my computer. But a few of these things bog down occasionally on Binder. You can comment out the parts that render maps, which we'll show you in a moment. And then the only other thing is, we'll get into this when we actually start running code, but if you want to run something, you just click into it, and at least on Windows that I'm running, Control Enter does it. You should also be able to see, you can hit this play button here and it'll run the cell as well. Any questions before I start talking spatial data? Okay.
I'll just mention I did test on a Mac, and Control Enter works. I always do Shift Enter or Shift Return on my keyboard.
Yeah, I was noticing that that's what it said to use up on the play button here too. So maybe I'm doing it some weird way that's just supported.
Yeah, I also tried for fun Command Enter. It's the special Mac key. That also works.
Great.
Oh, so I think Control Enter just runs the cell and stays in the cell, and Shift Enter jumps to the next.
Wonderful. Thank you. Yeah, and that's so the other thing I wanted to mention in noting this is new material is this is actually not the way I usually work with spatial data. So I've used the libraries we're using before, but they're not the thing I spend most of the time in. I don't always work out of a Jupyter notebook. And so, yeah, I appreciate if you have tips, or if you're like, hey, I use that library and there's like another way to do that, feel free to bring it up, or even better, make a pull request on the repository after the tutorial's over. I'd love that. So, but like I said, the spatial concepts will all translate. And if you are trying to learn how to do this stuff with these Python libraries, you should be able to take something away from it still. Okay, so let's talk. We frequently talk about GIS when we're talking about spatial information. And there are a lot of definitions of GIS. Some people would assume GIS is a specific software package. A company called Esri would really like you to assume GIS is their software package, ArcGIS. but basically give it away to universities so that we train the next generation of people to use their software. And I like it. I think it's great stuff. But there's a lot of other really great stuff out there too, including the packages we're going to use today. And so I take a pretty loose definition of GIS, or spatial information systems, geographic information systems. And just say that it's software and data that enable us to ask and answer questions involving where something is and how that location relates to other things. For you all, this won't be some paradigm shift. You're used to probably doing this in other contexts with other types of data. And so this is really just sort of a new component of doing that same type of inquiry with a specific type of data that has its own fickle points that you'll want to know about. And as I noted here, there's no reference implementation for GIS. It's not like there's not one standard. There are some standards that are part of it, but it's more of a really huge ecosystem than it is a specific type of thing. So it's a loose definition. And for this type of audience, I'd say, how is spatial data different? A lot of spatial data comes in a tabular form. It typically comes, I note here, it's in two forms. I'll mention a third one, but we're not going to do anything with that third one today. But if you've worked with tabular data or you've worked with image data, spatial data is almost just an extension of that references those pieces of information to some locations on the Earth. There are a few conceptual differences, though. So tabular data that has spatial information can be joined to other tabular information with spatial information. So if you're used to attribute joins in databases or in data science approaches, we have spatial joins, which sounds like it's just a single new concept, but it's almost like a whole new universe of concepts, because you're talking about overlaying information in space, and spatial relationships aren't just, are these two keys equal? It's, are they close to each other? Are they overlapping a certain amount? Are they overlapping in a specific way? Do they share a boundary? There are all kinds of ways that you can join information spatially. And as I note here, I think it's deeply powerful, and it leads to a whole new class of questions and answers. I think of it conceptually, and many of you are gonna be like, that's not right, Nick, but I think it's almost like adding a whole new dimension to your data. That's not like some spatial pun, but I think about how when I learned how to work with tabular data, that opened up this new universe of questions and capabilities. And then once you add multi or n-dimensional tabular data, that has its own approaches and its own sets of capabilities and questions and answers that you can do. I think spatial data is really similar because it requires a disciplined approach that fits the spatial data itself and has a lot of unique idiosyncrasies and capabilities. And it opens up a whole new class of questions and answers. So yeah, a lot of things are related to overlaying information in space. And then item 2 that I mentioned, 2 of 3, is image data. So you might think of visible light images like satellite imagery, but image data in GIS is also a gridded data set. You could have a grid of elevation values or precipitation values, all kinds of climatic information. Anything that is a set of values in a grid, we call it raster data. It's image data or grids. And they're referenced geographically to overlay them in space on the Earth, and also potentially with your other images or tabular data. And then that third one that I said I wasn't going to talk much about is point cloud data. We increasingly have a lot of point cloud data, LiDAR being a core tool for this, where you basically shoot lasers at things and you get their distance, and you get other properties about them like their color. And so point clouds are commonly used for constructing 3D models of items of interest, whether shot from overhead, from a drone, or from an airplane, or a terrestrial LiDAR on the ground. So I wanted to mention that in case some of you are like, oh yeah, I might need to work with some of that. We're not covering that today, but a lot of the same concepts will apply. You'll just use a different tool suite than we're talking about today. Any questions, comments, thoughts on that before I move forward? Okay, awesome. And just to kind of help us conceptually get our heads in what can we do with spatial information, I like to include potential questions we can answer with spatial data. So the most basic being what exists at a certain location, what's there. So we're familiar with maps. Maps answer the what's there question. But we quickly get into where or when you can get multidimensional, often time-based dimensions, spatial data. Where or when are certain conditions satisfied? So we can start to do some modeling with information. What has changed in a place over time? What spatial patterns exist? We do clustering, hotspot analysis is common. We can start doing what if analysis, getting to that modeling and hypothesis testing. We can look at variable interactions. And then we can start to answer questions of why and how, but we need to reformulate the question, which again, you're probably familiar with from other areas of research. Okay, so jumping into like, how do we actually work with spatial data? For Python, there are a few core packages that underlie a lot of other work. These are the big ones we're going to use today. We actually won't even import GDAL, but I mention it because it's everywhere and you basically need to get it installed, and it's a pain to get installed. I have a whole section at the very end for helping you get it installed on your local machine. And that's a big reason we're using Binder today, is because I didn't want to deal with people trying to install GDAL and GeoPandas on their computers. That would have taken up like half the workshop. But these are really wonderful tools. So GDAL, Geospatial Data Abstraction Library, it's compiled C or C++ code, and it's in almost anything that works with spatial information. And it's kind of a Swiss Army knife. It reads and writes like every format of spatial data, and it does a lot of the basic operations. And so it's really handy. It works on the command line. In Python, you can import its bindings directly, though I don't recommend it. Even the people I know who are like absolute experts in it are like, just don't touch it directly. Use a wrapper, or use something else. But it's very powerful and it's very fast. So it's really handy. So I wanted to mention that's a potential resource for you. The command line's not so bad. The command line's better documented and is pretty great to insert into workflows. And frequently people who work with GDAL and Python will do a sub-process call, a command line call to the GDAL command line rather than importing the Python bindings for it. There's also Fiona. So GDAL works best with gridded data, with raster data. Fiona is similar for that tabular data I mentioned. We call it vector data. And it reads and writes those formats, gives them to you in data structures that you'd be used to if you work with Python. Today, we're going to focus most heavily on GeoPandas and Folium. And GeoPandas builds on the capabilities of these other libraries and gives us pandas data frames. For those of you not super familiar with Python, pandas is a package that gives you a data science data structure, tables that you can manipulate, visualize, subset, query, all of that right in memory in Python. And it has a strong ecosystem around it, great documentation, lots of questions and answers on Stack Overflow, and GeoPandas extends that paradigm to support spatial information. And then Folium is a package for making maps. So almost every map we're going to plot today is a Folium map, and they're pretty handy because they're really familiar little web maps, and they work really readily with GeoPandas data frames. And rather than being us plotting just an image, you get a map that you can zoom into and pan around and click on. So it's pretty handy when you're learning this information to have access to a map like that. I think it more completely models the environment that you would get if you were using like a desktop user interface for it. Okay. Any questions about what I've covered so far? Okay. Well, so here's where, everything I've done.
Hey,
go
Nick,
ahead.
we just had a question pop up about CartoPy.
Yeah, I don't see that one. Where is that?
In the chat, it just popped up.
Huh. Where's my chat window? That's why I don't see it. Okay. Yeah. So there's a whole other ecosystem out there of excellent tools. I've never used CartoPy, but I've heard people talk about it. Do you like it? Would you recommend it? Excellent. Cool. I'll add that at the very end. I have a whole set of other things to potentially use and some package documentation. I'll make a note of that there too, and just include that for reference. So thank you. Anything else?
I don't see
Okay.
anything. Yep.
So this is the part where following along might be useful, or if you want to start modifying code or playing around with it, you can. Everything so far in the notebook has just been text, but if you are running, if you're running the notebook in Jupyter Lab here, this is where you can start to run cells. So again, I know a few people have come in since we loaded up. Here's the link to the tutorial information, and at the bottom of that README, there's a link to open up this notebook so you can get caught up. And we haven't run any code yet, so you're not behind. So all we're going to do right now is use Folium to show a map. This is pretty simple code here. You probably don't need to have ever seen Python before to see, okay, we're making a map, not like a map like task in a program, but an actual like cartography map. We're putting it at this location. You've probably seen coordinates before. These are latitude and longitude. And then we set a zoom level. And in the comments here, I note that it's important to get used to this. We have packages in Python that use latitude, then longitude, and some that use longitude, then latitude. This is roughly y, comma, x conceptually, but we say latitude and longitude. So some things like to do that, and other things are like, no, we're used to x, y, so we should do longitude first. And then I say it's roughly because these are angular coordinates, which we'll get into later. They're not Cartesian coordinates, so that it's not really a direct translation to x and y. It's close. You can treat it like it. And then these zooms are powers of 2. So zoom 1 is like the whole Earth. Zoom 2, zooms in by power 2, and higher numbers are more zoomed in. So if I Control Enter. Oh, and it wants me to start up a kernel here. And when I do Control Enter, it's okay to just use the default here. Click Select. It'll boot up Python for me and run my code. If I Control Enter again, I guess it'll run my code. And show me the output, which is I imported the package, I made the map, and then in a notebook, the last expression I evaluate, if I don't assign it to anything, it treats as a sort of print call, and it'll display the results below. So I just made a map that shows OpenStreetMap data, rendered tiles over University of California, Merced, where I work. Although that's not where I am. I'm in Sacramento, California. But I think this is also something that my colleagues will use, and so I thought it'd be nice to give them a little nod. And note that you can zoom in and out, you can pan around. These are all features of Folium maps and features of maps that you've probably gotten used to over the last like 2 decades of web mapping. So you get the basic capabilities you expect in a map right away. This is all we did. 3 lines of code will give you this. If you want to start playing with it, if you know, I think it's kind of fun to, if you kind of know your latitude and longitude, see if you can put them in, maybe set the zoom out a little bit, maybe zoom out to 12 and let's see if I could find Sacramento. It's like negative 120.9 and maybe like 38.4. Let's see. Oh no, I missed. Sacramento's right over here. So anyway, if you want to just play with this, get used to tweaking some parameters, feel free to change these parameters, run it a few times before we move on. And then I've tried to sprinkle documentation for some of the things I'm using throughout here. There are times when I was moving fast to try to develop parts of this and I didn't do that. So it'll be hit and miss. But if you want to see the documentation for just the Folium map, that information is in this URL here. So feel free to copy and paste that if you wanted to look around for more information. Nothing too complicated yet. Any questions, any thoughts? Okay. Well, great. So now we're actually going to do things with our map. So let's talk about sort of spatial data primitives almost. And there are specific classes that we are using, but these are definitely concepts that apply in almost any GIS, saying GIS system sort of like ATM machine, but I'll probably say it. Any geographic information system will have really similar sets of concepts. And the underlying data, the storage formats that are for interchange between these systems almost always support these exact same types of primitives. They might call them a different thing. Esri that I mentioned before, they like their tabular spatial information called feature classes. Other people are like, no, those are vector data sets. You could think of them as data tables that are spatial. And what's in that spatial information comes down to this consistent set. And almost all of it starts with points. Points being pairs of coordinates. Almost everybody calls them points. Some people call them nodes. Depending, a lot of people who work in like directed graphs or something like that like to call them nodes. And almost everything builds out from there. People connect these points together. People will attribute the points or connect the points and attribute the whole connected structure with information. But if we get started by understanding the coordinate pairs and the points, we'll have a good foundation. Although we're gonna continue using longitude and latitude. I'm already expressing a preference here that I tend to prefer X and Y. Y, but call it whatever you like in whatever order you like. So we're using those here because that's easiest when working with web maps, but it comes down to what coordinate system you're using to reference to the Earth. And we're going to talk more about coordinate systems later. They're usually the thing that I make people wait like a few days into a course before we start learning, but we have 3.5 hours, so we're going to learn about them today. And so you'll note I'm importing a whole bunch of, these are Python classes for points, multi-points, line strings, multi-line strings, polygons, multi-polygons here from a package named Shapely that I didn't mention before. Shapely does spatial operations on data. So it can slice and dice your spatial data. It can query your data. It underlies a lot of querying capabilities in GeoPandas that we're going to use today. So we're gonna just start by creating 2-point objects here in Python. So we do point, and then we do some coordinates. And note that this is not my preference. This is the library author's preference. These ones are longitude, latitude, where up here, this is Folium goes latitude, longitude. So we go. You got to pay attention to that, because I noted in the comments, it definitely threw me off for too long while developing this lesson. I was like, why are these points not showing up on my map? Because I had copied my coordinates from up here and was working with them. And so definitely need to be paying attention, because it's really easy to be like, the coordinates are right, and forget that they're swapped. So I defined 2 points here. They're pretty close to each other. You can see that just visually. And then I define an optional marker. This is what the points will look like on the map. You don't have to do that. Folium will just display it with the default. But we're saying give our circle a radius of 20 and fill it with orange, make it semi-transparent with like a black outline. And then we say, this is where we're going to get into maybe a little bit more technical capabilities here. We're going to add it to the map. And to do that with Folium, we call folium.geojson. And I'll describe that in a moment. We pass in our point. We tell it how we want it to symbolize it with marker equals marker. And then that creates the actual object. And then to add it to our map, we do .add to web map. And that's not some special name. That's just the name we gave it up here. This object still lives, even though we rendered it. We can keep adding items to it and re-render it, and it'll render below the cell here. The other thing I want to note, so GeoJSON it's a text-based format. If you've used JSON JavaScript object notation, GeoJSON is just sort of a specific structure of JSON syntax that includes the ability to store spatial information. It's handy because it's human readable and machine readable. It's also a very limited format, and so I don't recommend it for everything, but it's useful in a lot of cases, especially when working with a web map. And this function, we're not providing a GeoJSON object to it. We're providing a Shapely point class, and handily it'll convert it for us. So we don't have to do any conversion here to get this to work. It just, we pass it in, Folium will convert it to GeoJSON for us, or we could have provided GeoJSON as the argument to this function. At the end, we just call web map again, and it'll display it. So if I do enter or control enter there, because I made my coordinates different before, we're still looking up here. So I'm going to zoom out and go down to Merced here. If you happened to change your coordinates before on your map as well, these coordinates are basically the same as they were. These coordinates will get you to UC Merced. So you could go copy those, take them back up to your map initialization, swap them. Don't forget to swap them. I'll set the zoom back down again to 16, and then I'll run it. And that gets us back to where we were. And now if I were to run this again, it would automatically zoom me here. But if I run it again, it will also add new points to the map. So I don't necessarily need to do that. So I have 2 points on the map. One of them is the first point I created here, and the other is the second point. It looks like I can click it I can't because I didn't add any of that functionality, but there are some tools that will do that for you. Or you can manually add some click to make a pop-up functionality. So we'll see a little bit of that later. Okay, so I started covering some actual new information here. Any questions or I'll just pause for questions right now. Yeah, and Mark noted in the chat, you could try using keyword arguments instead of or defining your latitude and longitude as variables, and then do point lat and long so that you more readily see that you're putting in a specific order as opposed to just seeing the coordinates there and thinking everything's all right. Is that what you were saying, Mark? I like that approach. That's a good idea. Yeah, thank you. Any other questions, thoughts, recommendations? Okay, well, feel free to keep them coming in the chat as they keep going. I'm going to close the door for one moment. Just give me 1 second. Great. So we created 2 points. It's not super impressive. It is kind of fun to start adding stuff to a map, but we haven't done anything super useful yet or really understood spatial structures. But this is where we can start doing that, where lines work the same way. Again, lots of systems, they're basically just a string of points, or not a string, but a list or an array of points. And if you tell it it's a line, it will connect those points together with lines to make them a line, and it'll treat it like a line. So it's really just you define all the vertex points in your line and you get your line. So really similar set of concepts here. I'm just going to run this again, and we see our lines right on the map here, where it goes from the same point we were at, with the same points we put on the map, so the other point, but this time it's as a line. So not too much of a new concept in here. Same type of thing, full image GeoJSON, but we pass it the line string object instead of the point object, and it converts it. It adds it to the map. We display the map. Okay. So now that was a single segment line. We can do much longer ones. Again, we're not usually constructing these things manually. Usually something else is writing them out for us, or we have a reason, or we're actually clicking on a map to create our lines or points or polygons. But just to see conceptually, and also that you can do this. It's pretty easy to put these pieces together in code. So we have a full list of all of our points here, the 2 we defined before as UCM point and second point, and then our third and our fourth point all together in one Python list. And if I pass that in to a line string class, it'll, and then add it to map, we'll see this multi-segment line that goes, it has different directions depending upon the segment it's on. But I had a point here, a point here, a point here, and a point here, and it just connects them all as a line. But this is where we can see, again, the difference between that all these things are just coordinates, but it's really what we tell the computer it is. If I, instead of saying it's a line string, I take that same points list we just defined above and call it a polygon, we get a filled area. So I didn't add any more points. I didn't add this segment of line, but because I told it that these 4 points were a polygon, what it does is it's just symbolizing it this way for us, but it assumes that the polygon is closed. So it basically makes it go back to the beginning, and it assumes it has area. And so we can see this kind of faint fill on this polygon by default, which tells us, oh yeah, this is a polygon, it has area. This is not just a line. I could do 5 points, 1, 2, 3, 4, 5 to get the same effect of the outline with just a line, but that still wouldn't have area unless I say, no, this is a polygon. Any questions about that?
I have a question.
Yeah.
If you were to give the lines in a different order, so they weren't kind of along the polygon in that same order, it kind of zigzagged around, would it create the same polygon?
Yeah, so let's do that. Let's take this, copy it down here. And so if I were to swap, say, if I were to swap, like, debating which ones to do here, it's possible that it'll give me something invalid. So if I do a line version of this, it'd probably be fine. The lines can cross over, but with a polygon, it probably won't like it. Well, some systems will not let your segments cross over each other. It may not save out to certain file formats because this would be an invalid geometry. If these were 2 separate polygons that happen to touch at a vertex here, that'd be fine. But the line crossing over itself, or a boundary line crossing over another part of the boundaries, a no-no. It'd be an invalid geometry in a lot of spatial data systems. Did that answer your question? Or
Yeah.
okay. But yeah, the order of the points does matter in how it constructs both the line and the polygon. It won't automatically find what order they go in order to create sort of a bounding polygon or anything like that.
Thank you.
Any other questions?
So sort of there should have been like some validation from our end, like probably some packages that might help us with that.
Yeah, and this is where I don't, like I said, I don't work with a lot of these exact tools regularly, and so there probably is a validator. Most spatial data packages will do some validation on that for you. They'll complain about this. I would expect this to fail. I'm not positive, but I would expect it to fail if I tried to write it out to a lot of file formats. Or at least if I wrote it out and then tried to read it back in, something might complain. But I don't know what validator to use on this in Python. It's possible that Fiona or Shapely has a validation function. Those are the 2 packages I would look at. And I'll note that down. Just as when we take a break, I'll take a look and see if there's one. Okay. Any other questions right now? Okay. Well, and you'll note I've been plotting all these to the same map, and so everything's starting to get a little cluttered. We'll create new maps in a moment. But it's handy that you can keep running and adding stuff to the same map, but it's also nice to create new ones. So and then I love some space for practice. I might we might pause for, I'll check the schedule and then maybe we'll pause for about 5 minutes while we and let you all go kind of mess with your own maps. I have a link to the documentation for the point markers. So the these here down, what is, I don't even know what cell number this is. Just under this practice heading. So I have a link to that documentation, so you could go try to change how the points are displayed on the map. And let's see. So in terms of time and anticipated schedule, we're okay. Yeah, how about let's do 5 minutes of you not having to listen to me. Play with adjusting some of that display information or anything else you want to test working with here. And then, yeah, the nice thing is if you get into a state that you don't know how to go back from, just load up the GitHub repository again, click the launch binder link, and run the code again. It's pretty safe to mess with. So yeah, we'll give it till 2 minutes after the hour, and then I'll come back on and talk. But you can ask questions in the meantime, or just feel free to practice in your notebooks. Mark, are you referring to this background layer when you're talking about the data source? Yeah, so all of this stuff being displayed here, that's not the polygons that we're creating. Yeah, so the question in the chat for those of you who can't see it right now is, do we know where the Folium data source is at? Is it in the local Python library, or does it make an API call out to the internet? Yeah, so these are rendered tiles coming from, this one's coming from OpenStreetMap.org's servers. They have, it's not, I mean, it's not really an API call, but it's like not an API call. There's a specific structure to map tiles on the internet that it conforms to. And so if you know the server that has the tiles, and you know the zoom level, and then the X and the Y, location in the tiling scheme is not latitude and longitude. It's the tiling scheme that they're conforming to here, because these are all, this is actually, it looks seamless, but it's all a bunch of individual images. You can see them loading in, right? As I pan, you'll see the squares coming in. So the tiling scheme matters, but it's basically slash, I think it's like zoom slash X in the tiling scheme, Y in the tiling scheme. And you can, Folium has the ability for you to specify other background layers here. You would specify it usually, I think you could specify it right in the map constructor up here, but you can also add it to the map later, just like we're doing .add to web map. Folium has the ability to say, okay, I want to add someone else's map tiles to my map. Did that answer your question? Yeah, Folium, I mean, it needs an internet connection to work the way we're using it. I'm not 100% positive. You'd probably get something weird if it was failing to load up a background layer. I would say that if you, I would say you would use Folium if you have an internet connection. We're going to plot some objects without Folium later. And so Folium's nice if you want to interact with the data, and you do want internet connection usually for that. But there are other ways of exploring spatial data in Python as more static plots that you might use if you didn't have one. But I can't say for sure that it won't work if you don't have an internet connection, because it might just not show this background tile, but still render the data that you are putting on the map. Okay, another minute or so of kind of working with the data that you've plotted on the map. And we'll continue. Feel free to keep asking questions. Okay. Unless anyone pops in the chat and is like, give me like another minute. I'm gonna keep moving, and I appreciate you all hanging with me here. I know it's a lot to listen to one person for a while. I usually like to do like 30, 45 minutes of me talking, followed by like a similar or longer amount of time of like you working through an exercise. But that's in a multi-day classes. But it really does help to cement it when you get to do it yourself, as I'm sure many of you know. So we're kind of in the in-between space here, running it ourselves, but not writing our own code or following some set of instructions. But if you have time after this and do want to cement some of it, I'd recommend maybe working through the notebook without me talking as a second pass. It might make sense, might give you some freedom to try some things. But I know we're all just made of time, right? So plenty of time to do that twice. Okay, so far we've talked about spatial data. We've seen some web maps, and we're not. Feel free to keep asking questions about web maps. I do a lot of work with web maps and also with OpenStreetMap data in particular. But I'm not really covering those in this course. So if you have an interest in those components or anything like that, I'm happy to answer questions, but we're not going to dive deeper into those. But we've taken a look at a bit of that. And then we've created some basic spatial data. It's spatial data, but it wasn't at all meaningful to us. It was me choosing some coordinates. And it didn't say anything about the space it was at. It just said, here's a point on a map. So let's change that. Let's start to get into meaningful spatial data and what that structure looks like, what we do with it. And I note here, we had the spatial component of spatial data, but not the tabular or descriptive components. So when we think of spatial data, it has the location, and what we just had didn't tell us anything about that location. But this is where I start to add those database concepts on. You'll probably hear me calling it more and more vector data as we get into working with this, because it's going to start to fit my mental model of vector spatial data. But what you can think of it as is it's an attribute record that applies to the whole item. So if we think of each object we created here, each polygon or each point, it has its own record in a data table when we start to have a full model of spatial information. So the schema of those records is flexible. It could be whatever you want it to be. You could have whatever columns make sense to describe your spatial data. It's not like one spatial data format's like, you have to have a name and all this other stuff. It's whatever you like, just like databases. But I'll note that most data formats want you to stick to a single type of spatial data, space or vector data. So only points, only lines, only polygons in each data table you create. And most of them, not all of them, we'll note one that's a little different at the very end. But conceptually right now, consider that they should all have the same set of fields and attributes in one data table, even if some of the values are null. So if you think of it like almost every other data table or database you probably work with, you have your columns that are the same for every record, and you have rows that are all your records in the data table or database table. It's the same thing like that, and add the spatial information as a field on there. And conceptually, it looks a little like this. We This is from the GeoPandas documentation. So they have this index field here because that's how Pandas works. But if you think of it as your data table and your geometry column is another attribute, that's a pretty solid mental model for a lot of spatial data. You have the descriptive information, and there are these fields, and it has this descriptive information describing this spatial object. That might be a single point in space. That might be a polygon. When you're talking about a polygon, usually this is some sort of generalized information about the polygon. So let's say the polygon is this area on the map. Somebody said this is natural growth or something like that, and that's this whole area. We know that that's some generalization of reality, that whole area has some heterogeneity, but that generalization fits our data model here. Does that make sense? I don't necessarily feel like I 100% explain that, but does it make sense how we can basically add this geometry column onto existing data tables, and that geometry can be any of our spatial data types as long as it's one type per data table? Take your lack of no's as a yes, which is maybe dangerous. But if you have any questions about that, great, thank you. Getting one okay. We'll keep working with this. Like this is one goal of this workshop, is that you come away feeling comfortable with this general data structure that we're working with. But we're going to work a lot with stuff that looks like this, and so it'll get more cemented. Okay. And then just going up, I'd inserted something as a summary of the previous section, but I kind of jumped here to talk structure. But since we're working with that vector data, I just want to note we have that vector data, the spatial information can be translated, or polygons can be scaled or stretched or buffered to add more area. And we don't lose information on the attributes. That's an important characteristic of this data, that operations on the geometry column don't have to affect these attributes. They might in reality affect those. If you were to change the information in the geometry, you might say, well, one or more of these attributes are now invalid because the geometry changed. And so the area referred to by my polygon, for example, is now different. And I can't assume that the descriptive information about that area is valid anymore. But it can also stay the same. It's not automatically changed. And because the other primary data type for spatial information, raster data, image data, the data and the spatial information and the values are inextricably linked. So when you change one, you change the other, typically. So I want to point that out, that's a feature of vector data. We can change the geometry without changing the attributes or the descriptive information about that location in space. Any questions about that? Okay. Stop me if you do have questions. Okay, so let's get more hands-on, and we're going to start by using GeoPandas here. So we're going to import the GeoPandas package. GeoPandas is a beast to install, but it's not that bad to run. Again, more stuff on installation at the end. What's pretty cool about some of these packages in Python is you could just provide them a URL to the data source, and it'll download it and open it as if it was like an extracted zip file on your machine. So I think that's pretty handy. I almost never use that, but I try to remind myself to use it when I'm trying to teach. That can be dangerous for reproducibility, and so I don't always do that, but it's a useful feature at times. I did archive a copy of this, especially also if we ended up with a very large workshop, I thought it might be rude to hit their web service with like 50 people at once. But so this repository in this data folder has the download of that URL. So if you want, you can try changing this text here to this, and it'll load up the same thing. But that's just to say, GeoPandas can read from a URL, it can read from a local zip file, or it can read extracted zip files on your computer. I don't have to tell it what type of data it is. It does some introspection to figure it out, which is also really handy. So it's a pretty low barrier to entry. If you're like, hey, I'm pretty sure I have some vector or tabular spatial data and I want to work with it, you can just do geopandas.read file, your file, and it'll load it up. So that's pretty nice. And then I debated about this line because I was like, the people who work a lot with data frames might have a bone to pick with multiple things I'm doing on this line. But basically, I'm just saying, set the index on this data frame, the thing that we can use for quick querying, joining, and slicing and referencing, to a specific field in this data set that we'll see in a moment. And I'm telling it to keep the field as well, which creates some problems for us later that we're going to just work around. And then I tell it to do it in place. So I'm having do it on this existing object rather than returning a new object. And then the last thing I do is GeoPandas and Pandas both have a head method that will display the first 5 rows. And dang it, did I lose my kernel too? Okay, so if you lost your kernel, selecting to start the kernel, their documentation says it only does it if your browser tab's not active. So I was hoping that it would be fine, but we may need to import Folium again later, but we can do the run all above the cell here. So I'm going to do kernel run all above selected cell just to make sure it's caught up to where we're at and that I have everything imported since it restarted the kernel on me. And we can watch the progress. Okay, supposedly it didn't, maybe. Well, we'll find out. There's nothing too important already imported that we can't work around later. And then I'm going to run this cell with Control Enter. And this takes a moment because it's retrieving the data, reading it in, and then it's going to show me some results here. And so we get to inspect the data. I'll note that it might just be my version of Jupyter Notebooks, but on my computer, when I was running this outside of Binder, it doesn't give you this horizontal scroll bar. And so if you run into that same sort of thing when you're working out of a Jupyter Notebook, you might need to like do print basins.head. And it doesn't give you nearly as nice of a display, but it'll show you all of the fields involved and some sample information from them. So I can see this is the index that I set here, but I can also see that that's still a field here. And then just some other information about this file. I haven't told you much about it other than that I named this groundwater basin beta shape file URL. So we're probably working with some groundwater basins. And these are the attribute records. And we can see that data structure I was talking about, where the geometry field, it represents the geometry for us in text form. It's not necessarily, it might be stored this way, but it's not, actually it's not, because this is a shapefile format. So underlying, it's not stored like this. This is GeoPandas reinterpreting it into a GeoPandas data frame and then showing us a text representation of this geometry for us to see at a glance. But all of these attributes correspond and describe this geometry here. All of these ones correspond and describe this geometry, just like we expect with other things. But this is sort of like this is almost like a compound, I don't know how to describe it, data element. And you can, I guess, think of the geometry as describing these things as well. But typically with spatial data, these things exist as almost like properties of the geometry element. So we're not going to go through this function too much. Mostly, you can come back and read it later, especially if you know Python. But mostly, I just want you to run this. And this is a shortcut function that I made that will let us map geodata frames in one line and handle a few pieces for us. GeoPandas has some functionality for this that we'll use a little later. But I also think it's nice to be able to come back and see what we're doing as part of this too. So I don't want to dwell on this because I think it'll just confuse right now, but run this code because we will use it in the following cells. In the very next one, in fact, we've seen the tabular representation of this data we received, but let's take a look at it now on a map. So if I run this takes a moment because we're now going to draw a bunch of data from a geodata frame. And this function up here is actually masking quite a bit. But one thing that I'll reiterate a few different times is because there are many different types of coordinate systems, you can't overlay data, including displaying the data we downloaded on a web map, unless you align their coordinate systems. And that can sometimes be an expensive computational operation. It's not that slow, but in some cases, it can be one of the slower operations that you do in spatial data processing. Usually you want to be a little strategic about how you produce these things and get them to align their coordinate systems, but we'll talk more about that momentarily. So here's what our data looks like. We have groundwater basins in California. And if you want, you can zoom around and look at this data. You can see that the mapping utility is generalizing some of these polygons for us for display at low resolution. And then as we zoom in, not up there, as we zoom in, it will give us some more refined boundaries here. So yeah, but also note, again, I didn't configure anything that lets us click and get any information yet. GeoPanda's built-in utilities that we'll use soon do automatically configure those for us, or we could manually configure those. I also, that function has a layer control, so we can turn the data on and off as well. So that'll be useful in a moment. Okay, any questions about retrieving data, taking a look at a few of its records, or adding that data to a map? Okay, I know this is the long lead up. We haven't done a ton useful yet, but we're getting to the good stuff. So let's say I don't want to work with all this, and I don't because Binder has a limited computational budget, and I don't want to use all of it processing all of this polygon data every time we want to do anything in this workshop. So we're going to subset it to just these parts here in California's Central Valley agricultural region and get rid of all these complicated polygons out in the desert and High Sierra and on the coast. We can do that in a way that you're probably familiar with. Whether you've worked with Pandas, Pandas data frames in Python, or you've just worked with other querying and subsetting tools, we can subset to the basins in this data set that have a basin name, which we can see right up here. Basin name includes or is either Sacramento Valley or San Joaquin Valley. And if I run that, I can see that now I don't have any other values here, but before I did. And if I map that same CV basins object that I just created, I've now limited it to just those polygons in that area. That's maybe interesting. It's not a new spatial capability. It's a capability that many of you probably already had with any data table. That's an attribute query, an attribute subset. to the data. But it works on spatial data too, so that's cool. We can, if you already know pandas, you can do tons of stuff on spatial data and use a lot of your capabilities where they apply, and then bring in the new spatial information when you need it, when it's a GeoPandas data frame. But GeoPandas just extends pandas, so all of those approaches in pandas still apply when working with the attribute fields in the data frame. So I'll pause here before we start getting to spatial manipulations of this for any questions. Okay, well, as I said before, if you have a question, if I'm doing something that doesn't make sense, interrupt me, pop something in chat. I have the chat visible now. We are a small enough group that we can try to keep everyone on the same page. Okay, so I have a kind of verbose function. Again, we probably don't need most of this, but trying to just make clear what we're doing. And then we'll map it again. Basically, this is a little slow because, as I said before, it's having to align coordinate systems every time I map it. This spatial object is in one coordinate system, the map's in another. Again, I'll dive into that a little more later. But if we want to save having to align those every time we run the map, we can just one time align the coordinate systems. So I can reproject to a coordinate system that we colloquially call WGS-84. It has this code of 4326. Excuse me. We're not going to dive too much into these, but every coordinate system has this EPSG code that is one common identifier of them. Oddly, just as a trivia fact, this is, I think, the European Petroleum Standards Group. So somehow they assigned the identifiers for all spatial information. It goes back to European oil. I don't know. I don't know that history in detail, but just kind of an odd trivia piece. But these codes work in, again, basically like every piece of spatial software understands these codes. Some of that because almost every piece of spatial software has GDAL under the hood, like I said. But GDAL and this library called Proj, P-R-O-J. They all work together and align on this, but even without those, different things understand these as like an authority code. And all this function says is if the CRS, the coordinate reference system of my input to this function, my GeoPandas data frame, the EPSG code isn't already 4326, then reproject it. The toCRS function reprojects that transforms the coordinates in my data set into this coordinate reference system. Right now, I'm going to leave that as a little bit of like, what's he saying or magic, but we'll dive into that after we take a break, what's actually happening there. And because this, oddly, this is one of the main pieces you'll need to understand that will help you apply this to whatever other work you're doing. So all I'm doing here is I'm taking the full basins data set from before and reprojecting it, and we're saving it for later on when we're going to use it. And then I'm taking that same CV basins data set and reprojecting it here. I like to, and this is just a convention I follow, but honestly, I'd recommend it at least for things you write out to disk. I like to append this EPSG code to the end. And that way I just have a quick reference of like, what coordinate reference system is this in, whether I'm working with that as a variable in code or on disk, because there are lots of things that will automatically align coordinate systems for you, but there are plenty that won't. We're going to use one of them later. And having that signal that your two data sets use the same projection by having that code appended in your variable name or in your data set name on disk we'll save you time. Just like the suggestion earlier to call lat and long out into variables. This is just one of those signals that you'll get used to. Question in the chat: what happens if code is not 4326? That there are thousands of these CRSs, coordinate reference systems. It's totally okay for data to be in another one, subject to limitations we'll talk about later. But in this case, in order to align everything on one map, we're just standardizing on this, as that one uses latitude and longitude coordinates that we're familiar with. So if it's not that, it'll get reprojected to that in order to be displayed on the same map. Does that answer your question? Okay. Yeah, that stuff will all make more sense later. I'll have better examples for you. But that's what we're doing, and then we're just mapping it again here. And this time it'll be a little slower because it's reprojecting them, but then future calls to map this will avoid that transformation and should map more quickly. So nothing special here. We've seen this before. It comes out looking the same, even though we've transformed the CRS here, because this function was already doing it for us. And if it didn't, then Folium was doing it for us. Okay. So we subsetted these basins to the Central Valley using those attributes. But what if we pretend that there was no attribute value to subset on, but we still wanted to see just the basins that are in the Central Valley? We can do that. So we're going to get a new data set in, another file that I saved into that folder. It's saved as a zip file. You could have also loaded it up from a direct URL here, but now this is just the data source. So this is loading it straight out of this folder. I'm pretty sure it's a shape file in that zip file. Reprojecting it, and then instead of using our previous mapping function, we're using the built-in explore function of GeoPandas data frames here, or explore method, which won't be super fancy here, but you'll see a few differences. It's a little more computationally expensive to get set up, and it actually requires another dependency, but probably worth it. So the big thing you'll note is that if I mouse over it, it starts showing me some information and it highlights it. That's not super useful here. This polygon has two attributes, which are sort of almost just metadata, built-in metadata. But we'll use it later on something that has more attributes, and it becomes a really useful thing. So Explore sets up this hover pop-up for you and makes it a lot easier to look at your data than how we've been mapping it so far. And so what we're looking at here looks probably pretty similar to what we were looking at before, but this is a polygon. This is California's Central Valley alluvial boundary. So once you get outside this polygon, you start getting into places with bedrock close to the surface. But this whole area of California is basically alluvium, and that's why it's such great farmland. Okay, I don't think we did a lot new there. But I'll pause for questions. Any questions right now? Okay. So, like I said, let's try to, well, not try, let's get the groundwater basins that are in the Central Valley, but let's do it without the attributes. So note that we're starting with our basins, not our CV basins. So this is the original basins data that was not subsetted. And again, I note we need to make sure data are in the same projection before we do spatial operations. And what we're going to do here is we're going to use something called the spatial join. So like I said before, you could do attribute joins, which use some kind of shared attribute value to join two tables together. A spatial join uses the spatial relationship. We're going to do a really simple spatial join here, which is just do these two polygons overlap in any way. But it will transfer the attributes of one table to the other, just like with a tabular join that you're probably familiar with. So what that looks like is I take one GeoPandas data frame, in this case, our groundwater basins, and I do use its .sjoin, spatial join method. And I say, what's the other table I'm joining to it spatially? I'm going to use that Central Valley boundary. I'm doing an inner join. So it'll keep the attributes of both data sets, but it's only going to keep the geometry of one, and that's this one. This is the left table in this case, and this is the right table. But it'll keep the attributes of both, and it will match them where they intersect. We have some other predicates that we'll go through really quickly here, and then there's also an sjoin underscore nearest that will actually give you the ability to join not just when they overlap, but when they're close to each other with proximity. And other GIS systems have all kinds of ways of matching stuff in space. There's a ton of power here. This is a little bit more of a limited one in my experience in terms of the capabilities we have to do a spatial join, but it illustrates the concept well, and it can do the most common ones. So yeah, we're going to join, and we'll get back anything in the basins data set that overlaps this one via an intersect, and we'll keep attributes from both of them. And this looks just like what we did before, so that might not be that impressive, but we didn't do that with attributes. We did that fully based upon the spatial overlap between this and this. So it excluded all of this because it didn't touch the Central Valley polygon down here. Any questions about that? Like this method here is one of the things I really want you to walk away with, because it's the basis of a lot of concepts of overlaying data spatially, but it's also the basis of like every powerful thing you can do with vector data. They're all doing conceptually something really similar. Okay. Well, we're going to keep doing it. So you could yeah, question in the chat is right now it is intersecting two shape files. It is intersecting two spatial data frames. And I make that distinction from shape files because shape files are a specific file format. And we loaded these up. We did load these from shape files, so that's true. But yeah, we're intersecting two data frames here spatially. But an intersect in a lot of systems will actually modify the geometries, and this one keeps one geometry and transfers attributes from the other, just like a tabular join. Any other questions right now? Okay. So I'm running just a little behind, so I wanna I'm not gonna pause for this practice here, but in part because I also have code below that does this, but I want to show you what happens if we change this predicate here. So we can see what types of joins we can do by running, taking one of our geodata frames and doing .sindex.validQuery predicates here, and it'll tell us what our options are. So we used intersects, and the documentation will tell you what happens with each of these. Some of them are a little self-explanatory, but maybe not if it's your first time working with this. But we'll run a few others of these, and then we'll see the differences that it produces. For a data set like this, they don't all produce something super different, but depending upon your data, it might. And then we're just going to map all of them at once and provide names. That function we defined above accepts a dictionary with data frames and names, and that way they will show up once they've all been run. They'll show up in the layer switcher so that we can turn them on and off. And I guess the other thing I'll note while that's running is these query predicates are coming from Shapely. So Shapely is the Python package that we mentioned before that we made the points with. So we can see some overlapping here, but if we, sorry, I'll return to what I was saying in a moment. So if we turn all these off, we have the central valley boundary. And if we do the within method, what we actually see is not that many of them are fully within, but that predicate within says the polygon in the left table needs to be fully within the polygons in the right table. And so only a few of them are fully within. And if we go to intersect and we see all of them, and we were to zoom in, we could see that there's just some minor differences in the boundary. A lot of these things overlap each other on the boundary, but there are some minor differences in the boundaries that cause a lot of these to, like, take a look at this here, to maybe not be considered fully within. And so they get dropped when we do a predicate of within. So not the best data to demonstrate some of this stuff with, but hopefully conceptually shows you that you can get different results with different query predicates here. And same if we do overlap, which I'm forgetting now what that predicate means. We get different results than even the intersect method. So you can compare these here if you want and take a look at what's different between them. But if you really want to understand why, that's coming from Shapely. And Shapely's documentation has, at this link, at this anchor, you can find out more about what these different query predicates do. And that will help you in deciding what you would need to use for your own spatial joins to get the data that you want joined. So I'll open that up, but we don't have to like read through it. So those are binary predicates, but then we get to covers and covered by, and overlaps is that the one that was different before? Geometries have more than one, but not all points in common, have the same dimension, and the intersection of the interiors of the geometry have the same dimension as the geometries themselves. So, okay. So that's spatial join. What I often find is important for me when overlaying polygons in particular, because you could join points and polygons, you can join lines and polygons, you can join polygons and polygons, and then some of these systems have specific behaviors trying to join points and points, or points and lines, or lines and lines and stuff like that. You have to look at their documentation for that. But what I find I often like is if I have a lot of polygons that are inside of another one, and I want to, especially like, let's say I didn't have one Central Valley polygon, but I had like many regions of California, and maybe some of these regions sliced through some of these groundwater basins. Determining membership of each polygon between one or the other isn't a super straightforward answer. There are lots of potential answers. And if you're going to do aggregation, you don't want double counting of just saying, well, it's in both of them. That there are times where it's okay to assign something to two outputs, and there are other times it's not okay. So a technique I often like is a centroid approach, where we assign membership based upon, does the center of this polygon fall within the polygon that we're joining it to. There are tools that make that pretty straightforward, and here we kind of have to go a little bit backward in order to make that happen. But let's let's take a look at generating centroids first to see how this gets a little tricky. So we're going to import Shapely itself. And this is actually a snippet from the Shapely documentation. And if we run it, we see we're making a polygon here. We get a polygon centroid, and then we get this representative point. And note that these are two different points that are supposed to be more or less inside the polygon here. They're both attributes of the polygon. Or, well, this one's a method, as I know, but they're both information about the polygon. And they're different because if we plot this polygon, we see it's a donut. So the true centroid of this polygon is actually outside of the polygon. And that'll happen in lots of real data. That you might get something that's like a crescent moon shape or something like that. I work with a lot of agricultural field data, and plenty of agricultural fields are center pivot, circular-ish, and lots of them are just super weird shapes. It's kind of surprising given that we think of them as like squares and circles. That there are lots of random shapes, and the centroid of a polygon can fall outside the polygon. So oftentimes, if you want to make sure that you have a representative point for a polygon that is inside of it, there's a separate method for that because the true centroid may be outside. So Shapely calls this the representative point. Other tools will have different methods for this, but it's worth looking for. One thing you could do here too is, that I think is a little instructive is we're going to move on from it, but you could take a look at this code here and see if you can understand how it generates this polygon. And it specifically highlights a few spatial operations, including buffering points, basically taking a point or polygon and growing it, and then differencing, where you can actually do area-based operations on multiple polygons together. So it's worth taking a look at that and trying to understand it just for those operations alone. Any questions? Sorry, I look over here when I say any questions, because that's where all of you are on my screen. Oh, great. Well, I'm glad representative point helps. Yeah, thanks for the feedback. Yeah, and I'll note, so like both GeoPandas and Shapely both have, I think, pretty good documentation. Shapely's is, I think, a little more thorough. GeoPandas, you might need to look around a little to find what you want, but they both have pretty good documentation. But Shapely's is very thorough about, I'd say, in my experience, about the consequences of specific choices, and also about like the meaning of specific operations. You may need to go do other searches to understand some of the wording they're using at certain times, but they're documenting what's happening and why, and some of the consequences of it. Okay, let's keep moving. Then we're just about 15 minutes away from taking a break, and I think we'll be right about on time for that, because we're just going to run these cells before we go take a break. So what I want to do here is actually do something with a spatial join. So we did a spatial subset, but where these start to come into play, that's pretty nice, is, well, what if I want to take these groundwater basins and actually summarize some information about them based upon their spatial groupings, that these are all in the Central Valley. I wish I'd chosen different data sets here, because I wished I'd chosen one that sliced up the Central Valley a little more, so we had multiple polygons here overlaying these. But conceptually, the same operations apply. It makes more sense if we're actually trying to aggregate them into multiple bins. But I didn't do that, but we're going to go through it as if we did. Because maybe you want the total of some attribute in these, you want the total of some attribute in these ones, and you want the total of some attribute in these ones. We can do that by mixing spatial joins and some other aggregation operators. So that's where this stuff starts to become really powerful, is you can start asking questions of your data and manipulating it spatially. So I note a little bit about that here and what we're doing and why. But we're gonna make the Central Valley data a little more well behaved, because right now it only has some basic metadata. So we're gonna give it an identifier. And then we're also going to add our own area column to the groundwater basins. I did this before I was in a system that actually let me see all the attributes. And so, but we're going to add a SI unit area column too. And then we'll join the Central Valley to the groundwater basins one more time, and then we'll perform an aggregation with the dissolve. And dissolve modifies the geometries underneath it so that we get a new polygon with new attribute information that's an aggregate of the geometries that went into it. Not all systems require that particular operation for aggregation, but it's useful. So we're going to do those in order. So our first step is, let's take a look at that Central Valley data that we have and see that it's just the shape length and shape area. This probably came out of ArcGIS if it has these attributes. And then it's the actual polygon geometry. So not a lot there. Basically, this is almost an unattributed polygon. So we're just going to use standard data frame tool of, we're going to assign a new field to it, but there's only one record. So we can just set it to one value, the Central Valley. And then we will look at it again and we'll see, yeah, there's a new field with the name Central Valley. So this is our identifier in this case. And then let's attach the area to the groundwater basin. So even though they already have it, I think it's useful to see that we can pull attribute information off of the geometry objects as well. So this is where I haven't explained projections yet, but when you want to work with areas, you want to make sure that your data are in a coordinate system that has accurate areas. The one thing I'll say before the break about this is coordinate systems optimize for different properties, and some of them have to trade area accuracy for directional accuracy or distance accuracy. And we'll get into why that is. But there's a coordinate system optimized for California that also is optimized for accurate areas. And it's, we call it California Teal Albers, but its EPSG code is 3310. So before I get the area, I am going to convert my basins data, that again, that original raw basins data, not the subsetted one, to that coordinate system that has accurate areas, and make it basins 3310 here so that I know that I'm working with the right ones. And now I can do operations that involve the area of my geometry field and know that I'll get a pretty accurate number off of it. So I can say basins 3310.geometry. So getting the full column of the geometry object from that basins data set. And then for all of those, get the area attribute off of the geometry, which will be in square meters. You have to know that about your coordinate system. The units of it are dependent upon the coordinate system, and that you'll find that documented in places you can look this information up. I should put a link for that in here. Let me just make a note. And then, so I'm dividing by 10 to the 6th so that we, instead of getting area in square meters, we get area in square kilometers. And then I'm taking that new basically series that it's creating here and putting it into the field basin area square kilometers. And then we're going to take a look at it, but with, and actually in here, I'm going to remove the print because Binder shows it to us more nicely without that. And then I convert it back to the version that's more useful for web maps here. So it's now basin 4326 area, so that we know it's the version of that has the areas attached. So let's run that. And I think since this wasn't last, and I didn't print it. Sorry, I'm just rearranging that so that it actually runs and shows me the head of the table there. We can see that it appended this new column with the area of each basin, and we can see that it's roughly scaling with these other area measures that are already on it. So that's good. Any questions about what I just did or what happened there? Trying to balance not moving slow for those of you who are really experienced with Python and Pandas, or way too fast for those of you who have no experience with this. Okay, so we have an ID field on our Central Valley polygon on our valley here. And then we have our area field that we want to aggregate the area of the groundwater basins that fall within the Central Valley polygon. So we have our starting information now. Now we're going to do the join so that we can attribute all of these polygons, all of these records, to know whether or not they're in the Central Valley. So we'll get the Central Valley attached to them as being part of it. This is where it'd be more useful if we had multiple records in this, we would get the different identifier attached as an attribute here. So if it was like Sacramento Valley, San Joaquin Valley, we get Sacramento Valley, San Joaquin Valley as an identifier attached here. Again, we're not doing that. Sorry about that. But we're going to do the same join as we did before, but this time to the version that has the area attached, and also with the version that has this identifier attached. So same spatial join that we did before. After we do that though, so that gives us our Central Valley basins. We're gonna subset this. For the aggregation, I want just the valley name. So that's that new attribute, Central Valley, the geometry, and the attributes that I'm interested in aggregating. Because what we're going to do after that is we're going to run this dissolve, which will run the aggregation for us. It'll dissolve all of the polygons that share this attribute value as the same. So every polygon that has this attribute we're attaching in this spatial join, if the value is the same, they will all become one. And the aggregation function it will use on all the other attributes is sum. We could put mean, we could put, it defaults to first. It'll just take the value of the first record it encounters. But we're going to say, no, sum them all up to get the full area. So it doesn't run that on this, and this is the one it's grouping by, but it will run the sum on this. But I don't want it trying to run the sum on the rest of these. So we'll run that and then take a look at the head of it. So now we have just one polygon again. This was our basins, but it's dissolved again. And we can see the total area of groundwater basins that fall within the Central Valley is 53,000 square kilometers. And then just to do a little bit of final verification here, we're going to plot it. So we'll use that explore method, and we'll see that we can actually add multiple layers using the GeoPandas built-in explore method. So this is geodataframe.explore. We can give it a name, and then we can, instead of plotting it immediately, we save it out to a variable named webmap. And when we call explore on another item, we can tell it what map to use, what map to put it on. And then we can do some stuff we did before of adding the layer control to the web map. So we can start modifying that map just like we can any other Foolean map. And then we show the map. So let's take a look at that. Okay, so then these look pretty similar, but again, we have the layers named up here in the top right. So we have the dissolved basins and then the original valley boundary. And so if we go look up here, we'll see a point of difference here. So this is the original valley boundary, and here are the groundwater basins that overlap the valley boundary. So we can see that we did actually do something. This is just verification of that. And then we can see this is our aggregated groundwater basins that fall within the Central Valley. They became one polygon with 53, the basin area of 53,000 square kilometers. Or we can just go back and see the valley boundary here, which now has the valley name attribute attached. I think this is in some ways, like I said, almost a little too simplified. I wish it was a little more complicated because you could see the power of it if it was properly grouping these across more than one polygon. But does this make sense? Can you see what we did and why here? And then do you have any questions? Will spatial aggregations be of any use to you? Okay. Let's take a break. Let's come back at 12:15 Pacific, 1:15 Mountain, 2:15 Central, 3:15 Eastern, and we'll talk projections because we can't go into projections with me having just talked at you for a while. And then we'll work with some raster data and then wrap up. So I'll turn off my camera and probably my audio for the break, but I'll monitor chat, and then I'll be back at 12:15. Sound good?
Sounds great. Thank you, Nick.
Okay, thank you. Okay. Hopefully everyone had a good break. Are people back now feeling a little mentally rested? Any thoughts or questions come up as you thought about the things that we did in the first part of the workshop? Okay. Well, I'm gonna assume everyone's back now. Appreciate you all sticking with me here. I know that it's not as interactive as I usually like my teaching to be, but that's part of how I structured this. So we'll see. This might need a little reworking, but this next section is definitely more talking and looking and less running code. But this next section is pretty important for understanding one of the hidden pieces of working with spatial data and understanding the data itself. So like I said, I want you to be able to take what we're covering today and apply it to whatever your domain of expertise is. And coordinate systems, projections and coordinate systems are really one of the foundational pieces of that geometry column of the spatial information in these data sets that you should have a basic understanding of, enough so that you know when you're getting into dangerous territory, enough so that you understand a little bit of what you're looking at, and then can go find the right documentation later on. So coordinate systems, you'll hear me frequently use the term projections, which kind of colloquially is a word that people frequently use to cover the whole set, but they're not all projections. But it's often called the catch-all. We called that as a catch-all. They're a very critical part of it, all this. And over time, a lot of spatial software has worked to hide them from us, which is nice in some ways. Like, it makes things a lot more interesting and more fun when you can abstract away the parts of it that are kind of a pain in the butt, but it also lets us get into dangerous territory without even knowing it sometimes. So that area calculation I mentioned earlier, that's one of them. You might calculate the area off of data in another coordinate system, not knowing that it's inaccurate. There's not some loud warning that, hey, maybe you shouldn't calculate area off of this. It's not a good coordinate system to calculate area from. So you can get into dangerous territory without even knowing it. And that's where you need to have this basic understanding of projections and coordinate systems so that you can kind of keep yourself out of those spots. This all stems from the fact that the Earth is a sphere, and our surfaces that we're displaying maps on are usually flat. I've got this nominally a globe, inflatable globe. And I just want to point out, just you know this intuitively probably, but you can't flatten it. Like it won't go fully flat. This thing that's a sphere, you know, it's not just because this is a cheap plastic globe, but it's because taking something that is, you know, at its full surface shape, a sphere, and flattening it, it just won't go straight flat. You can also think of unpeeling an orange or something like that and trying to lay it flat on the table. What happens is the orange peel tears in specific spots, right, to get a little flatter. And we've seen maps like that. I feel like a lot of movies from like the 80s and 90s had that like map. I don't remember what projection it is. Maybe some of you do, but that has the breaks in it. But you have to do something to get the map to go flat, and that involves some set of trade-offs. And also a whole lot of math, which is where a lot of this derives its name from, is it's a mathematical projection. And I don't do that kind of math, so I don't know that part of it, but I rely on the people who did a very good job with it in the underlying libraries here. This is all complicated further by the fact that the Earth is not actually a sphere. I just lied to you, it's not a sphere. It's close to a sphere, but it's squished in one direction and also bumpy, as you know. And so for our purposes today, that just makes the math a little harder for the people doing the work underneath, because they can't just use spherical mathematical transformations. They have to have this actual mathematical model of the Earth's surface that then they're doing transformations on. Coordinate systems build on all of that. And they help us reference data on the surface of the real world to data on the surface of this model, and then basically unwrap it to a flat surface in various ways, which we'll call, you know, spherical surface like a globe, or a planar projection, being what's on your computer screen or what's on a map. So the other way we can understand it is what I mentioned earlier about how the globe has angular coordinates, or the Earth has angular coordinates, and planar coordinates are X and Y. So even just intuitively, there's not a direct correspondence between those angular coordinates and the planar coordinates. And so intuitively, you have to do something to get them to match up in some other way. And you can see that they're angular coordinates when you just think of it as, if you want to travel 5 degrees of longitude at the equator, that's a pretty long distance. If you want to travel 5 degrees of longitude up near the North or the South poles, that's very short. If you're actually at the pole, or a few meters away from the pole, you could travel 5 degrees of longitude in a step, right? And so that's the angular coordinate I'm talking about. The degrees of longitude don't have a consistent planar distance. It depends on the latitude you're at. So that hopefully helps intuitively understand also why we need to do something to unwrap this stuff to a flat surface. And that unwrapping is projecting the data. Yeah, then we'll discuss that part of it in a moment. So, I mean, you all have it right there, but yeah, what happens when we project data is we distort usually a few of these. There's usually one, maybe two of these that are pretty accurate, and then the rest are having some trade-off from some to significant error. So a projection, when we project spherical data onto a flat surface, we can preserve area as accurate, we can preserve distance as accurate, we can preserve direction or angles as accurate, we can preserve the shape of objects as accurate, or we could preserve the scale. But when we usually can't do more than about 2 of these in a single projection. You have some set of trade-offs where in order to get accurate distances, you might need to sacrifice accurate areas. In order to get accurate directions, you might sacrifice accurate areas and distances. Common web maps we're using up here, in order to get this displayed on the map, we're using usually a projection called Web Mercator. I feel like one geographic debate that constantly gets brought out of geographers' realms and into the realm of the rest of the world is like Greenland's not the size of Africa, right? It's not bigger than Africa, especially. And that's the Mercator projection. Mercator was optimized for navigation on ships. Directions are true. So angles are correct, locally, especially. But areas, not correct. So we can see that trade-off in this projection right here. You want to see what Greenland actually looks like. Where is it on this map? On this globe? Greenland's this tiny purple mass up here. And it's about the size of any one of the countries. Sorry, my blur on this thing's not any one of the countries in Africa here. Let me turn the blur off. So it's about the size of any of the countries in Africa, Greenland, right there in purple. But on this web map, they're the same size. That's a distortion from the projection. And there are a few things going on of why would we choose a map optimized for ship navigation for web map? Do any of you have any ideas for why are we even bothering to use this map today? There's a lot of criticism of it because of assertions it continues to project imperialism and other things, which are valid. But there are also reasons that people are using it. Anyone know? Well, if we think of the context that we frequently are using it in, it's actually not that different from the reasons it was developed in the first place. So, sorry, I just intuitively zoomed in here. I live here. I edit OpenStreetMap a lot, and so I'm just so used to zooming in here. But partially, I'm zooming into a grid of a city, and if you want to navigate, we are using these maps to navigate. And so using a map that has true direction, where when I look at the map, its directions are correct relative to each other and correct on the map. That's a useful feature. And locally, distances are correct in a Mercator projection. I didn't mention that before, but it means that within an area, the distances are true. And that's also very helpful on a map that we are using for the purpose we're using it for. And then the other thing is that the computation for the Web Mercator projection is relatively simple, and so it's optimized for speed of computation, and that's a useful feature for the people producing the maps. And so my point is, maps can be wrong, but that adage that you've probably all heard like a million times is, all models are wrong, but some of them are useful, from George E.P. Block. That really applies to projections. And really the thing is, you can point to what's wrong with any projection or coordinate system, but it has its purpose. Frequently, they'll even be optimized for a specific area of the world. There are global projections like the ones we were looking at. But that one that I projected to that was correct area, that's a California specific projection. It further optimizes things to be more accurate in California. And your areas of interest will have their own projections that you can find as well that people are using for increased accuracy in all of these. So that even if it's like, well, areas are correct, but these are wrong, these will be less wrong in your locally optimized projection than they would be in a global projection. So you have these trade-offs, but if you know what your purpose of your data are, you can choose the projection that is best optimized for that purpose. Does that make sense? Any questions about that? That's like number one mapping take home for projections. Make sure your projection is optimized for the purpose you are using it for. And number two is don't get in trouble while changing projections. Okay, if you have questions, as usual, interrupt me, put them in the chat. Hopefully you're all still alive out there. So, and not getting in trouble, I want to give you a quick overview of how a projection or coordinate system is built, complete with typos. Seeing a few of them here. Anyway, coordinate systems get complex pretty quickly. So I mentioned we have this Earth surface model, this mathematical model, because there's not actually a sphere, but it's close. We have latitude and longitude coordinate systems, these angular coordinate systems, and then we have these Cartesian projected coordinate systems that I talked about. How do these all fit together? Well, they're sort of a layer cake. A projected coordinate system is built on top of our geographic coordinate system. So our Cartesian coordinate system is built on top of our angular coordinate system. So its coordinates reference themselves to the angular coordinates. Those angular coordinates themselves are meaningless without some kind of anchoring to the underlying Earth surface model. And that's the datum. The datum is that Earth surface model and the other information that sort of anchors a coordinate system in place on the surface of the Earth. So I go into them in a little bit of detail here for your reference. Datums, that is to my understanding the correct plural. It's not data because datum's the term, as opposed to it being a singular unit. So these provide the way to anchor things. And modern ones, my understanding is they have a suite of control points, basically, that map the data on the model to the real Earth, that are derived. I don't know. The surveyors do that stuff. I don't do that part. But I just want to give a few examples. So we were using WGS 1984 above. There's also NAD 1983. That's North American Datum 1983. These are usually defined for the era that they were made. There are updates to these that are also available. And what I want to note is that if you get coordinates that someone says are in latitude and longitude, they probably mean that they're using WGS 1984. But latitude and longitude apply to those angular coordinates can be applied to any of these datums. And then the geographic coordinate system that's built on top of that. So as we said, it's an angular coordinate system, not really usable for display on a screen. And I want to note that the geographic coordinate system often has the same name as the datum. So WGS 1984 is both a geographic coordinate system and a datum with the same name. And when someone says WGS 1984, they usually mean the longitude and latitude based coordinates in the geographic coordinate system named WGS 1984 that is built on top of the datum, the Earth surface model with the same name. I say this because when you're choosing a projection, typically the first part of the projection is this geographic coordinate system and datum, because it's really important information for you, because transforming between geographic coordinate systems is a lossy operation in many cases. There are some very good models that help transform coordinates between those, but transforming between NAD 1983 and WGS 1984 has some error associated with it. And whether or not it's acceptable error will depend upon your application. Whereas if I want it to transform between two projected coordinate systems within that both are built on top of the same geographic coordinate system and datum, that's a pretty reliable operation overall. There's a little bit of error, but like it's small. It's really once you're transforming between geographic coordinate systems and datums that you start getting into some error. So that's why when we're naming these coordinate systems, they are often prefixed by their geographic coordinate system and datum. So you'll come to recognize this one and NAD 1983 if you do much work with spatial data. And then, as I said, there are dozens, hundreds of projected coordinate systems that cover any given region of the Earth. They're optimizing for a specific attributes, specific areas, specific working purposes. And they'll have their own origin points. They'll have their own units. You'll see projections that are in meters, some that are in feet, and they'll have their own methods of projecting that create those trade-offs. You won't ever, unless you really like make this your work, be an expert in all of this, but I just want to teach you to recognize those and to look for the right one for the job. Okay, before we start diving into a few examples, any questions? Okay. So one of the most common projections you'll see is what we call equirectangular projection. This is like the projection for unprojected data, which is basically if you treat the angular coordinates as Cartesian coordinates, you get equirectangular. If you treat longitude as if it's a true x value and plot it as x and y, you get this projection. It's relatively easy to see. It has some distortion associated with it. You can see Greenland again, should still be much smaller than that because remember the areas between these lines up here are vanishingly small, as opposed to down here where this is pretty accurate. The math is simple. There's no real function going on here, so it's really quick to plot. Both QGIS and ArcGIS, the desktop GIS packages that are in most common use, if you try to display data that does not have a projected coordinate system, that is not projected, but is stored just with geographic coordinates, they will display it in this projection by default. They have to project the data in order to show it to you on a screen, right? There's no option not to because they need some Cartesian coordinates. So they'll just do this because it's super cheap to compute and reasonable to display. So you'll see this one sometimes. The other one's Mercator that we just saw. Like Antarctica is tiny, and it's bigger than anything else on the map in Mercator. In fact, you have to cut off the poles with Mercator because it goes to infinity basically at some point. So, but as we talked about, angles are preserved. It's good for navigation. And the de facto standard for web mapping, Web Mercator, is optimized for calculation speed, as I said. I have to stop myself when teaching projections because the first like 10 times anyone learns anything about projections, they're like they're just super boring. And I'm sorry for that. But once you dive into it, they're like very interesting in how they're constructed. And you get into all kinds of interesting geometry and shapes and some cool innovative stuff that comes down to some simple fundamental building blocks. So I'm always like, I want to tell them how this is done, but you don't need to know that today. It'll take too long. It'll be too boring. But there's some cool stuff under the hood there if that's your thing. And here's another one. I think it's pronounced like mallweed. Maybe not. But it tries to compensate for some of the problems of the maps we saw before and keep areas preserved. But shapes are distorted, directions may be distorted. but you get accurate areas on a global projection here. So these are just a few global ones. Now, getting into a little bit more practical use, because lots of us, some of you may be working with global data, but lots of us are working with some kind of continental or regional data. And one of the most common across disciplines projections that I see is what we call universal transverse Mercator. Basically, it's you take the Mercator projection, which is pretty accurate near the equator. And if you rotate the method of projection so that it's pretty accurate north-south instead of east-west, and then you do a whole bunch of these, but you only keep the slice near the equator and make that a zone, and then you chop off the edges of it, you get universal transverse Mercator. So you keep a really accurate zone of Mercator, and you project this area separately, keep a really accurate zone of it, and toss everything outside of it, and do it again and again and again, covering the whole Earth, north and south, in separate projections. That's universal transverse Mercator. And so these zones matter because this is just a Mercator projection. So if I tried to show some data from Maine in we call them UTM zones, universal transverse Mercator, UTM zone for Northern California, this is going to start getting pretty distorted out here. It's going to have a lot of trade-offs because it's pretty far from the accurate zone of the Mercator projection, what we call our central meridian. But if I want to use UTM data for Maine, there's a zone optimized for Maine. I could use zone 19 instead of zone 10 and have very accurate data for Maine. So you'll frequently find data stored in UTM or interchange of data done with UTM, and just get to know what UTM zone you're in here. So if you work primarily in your local area, you'll see a lot of data. I work a lot with data in zone 10 and zone 11. Going one zone over, like if it's like, well, I have data that's in both of these states, you could probably store it in UTM and be okay as long as you're aware that like it's going to get less accurate. But going many zones, you're going to want to find another projection. There are projections optimized for the continental United States or the contiguous United States, and things like that. So look around for the one that matches the scale of your data. But you will see, you'll probably see data in UTM if you work at all locally. The other one that you will see a fair amount of is what we call state plane. You'll see this if you work with data coming from counties and states. This is frequently the data or the format used for surveying in local governments. So a lot of local data comes as state plane. It's kind of a pain, kind of confusing. Just know that you can project out of it to another coordinate system if it suits your purposes. So these are pretty accurate, 1 to 10,000 scale precision, or no more than 1 to 10,000, 1/10,000th of whatever your unit of measure is, could be error within any zone. So like I could know, like if I'm working in California's state plane zone 5, that values will not be off by more than 1/10,000th, which is pretty dang good for lots of projections. The rest of this stuff is basic, but note that it's a coordinate system, not a single projection. It's a series of projections that all have, or it's a series of coordinate systems built on top of one type of projection, and each state defines their coordinate systems and their projections. So, but I'm pretty sure this FIPS standard is national here for the error. Any questions about these projections here? I do want to note there are a few sites where you can find reasonable projections. There's epsg.io, which will let you find an appropriate projection. I'm pretty sure there's a QGIS plugin. There's another one that'll let you like pan to an area on a map and it'll show you the projections that are optimized for that area, but I can't remember what it is right now. Maybe it's this one. But this is a good spot to start as a reference if you have an EPSG code and you want to look up information about it, or if you want to potentially find a projection that's optimized for your area. Okay. And then I have this text here. These are the things I want you to come out of learning about projections with as you go into working with more spatial data. So as I said before, maybe it makes more sense now. If you want to work with two pieces of spatial data together and overlay them, they have to share a projection or a coordinate system. I can't compare latitude 38 with 4 million meters north from a different projected coordinate system. I can't do that unless I make one's coordinates into the other. And we call that reprojecting or changing the coordinate reference system. We were doing that earlier with the 2CRS function here, 2_CRS right here, or method. That transforms the underlying coordinates so that they match that other coordinate system. And then the other big error I see, or the big error I see people doing when they're trying to change coordinate systems is most spatial data packages or desktop GIS software will also offer a way to just set the coordinate system. So think of that as you telling it how to interpret the values that it already has as coordinates. You're saying, oh, those values are in this coordinate system. And if you tell it the wrong thing for that, then it's going to incorrectly interpret those coordinates. And so people use that functionality when what they want to do is actually transform the underlying coordinates, reproject them from one value to another, and change the values stored for coordinates. Almost every time you're going to want to use that reprojection, that 2CRS function. If your data is displaying in the wrong location, that's when you want to tell it to reinterpret the existing coordinates by using some of those functionalities to set the coordinate system. We're not going to do much of that today, but just know that if your data is displaying in the wrong spot on a map, you've probably used either reprojection or setting the coordinate system value incorrectly, or if somebody comes to you and asks you about that. And we haven't gotten to rasters yet, but as I told you about like where the accuracy and error comes in potentially with tabular data and coordinate systems. But when we get to this gridded data, the image data, reprojection of that data triggers a resample or a regridding of the raster. And you want to avoid that because that changes the data. Reprojecting the raster changes the actual values stored as data in that raster in almost every case, and you want to avoid it. And when you can't avoid it, you want to do it exactly once to get it into the coordinate system that you're going to use for every other analysis with it. And when possible, take your vector data and project it to align with your raster for that part of your analysis, and then bring the data back out of that back to your vector data or something like that. We'll show you some methods for that in a moment. So because vector data reprojection is relatively precise in most cases, but raster data, you're gonna lose some information. Does that make sense? Maybe it'll make more sense when we show it. Okay, and then I already covered 4 and 5 here. Any other questions? Any questions at all on anything we've talked about so far?
I just had a quick question. Like, if you're trying to change like the coordinate system, we just need to ensure that it's from the same the mathematical model, right? That's it. Otherwise, there's chance of like lossy like transformations, maybe.
Yeah, you don't need to make sure it stays the same, but you do need to be if you want to ensure it's very accurate, you want it to be built off of the same datum and geographic coordinate system. If you need, some cases you will need to transform it to a coordinate system built on top of another datum. That's just something that happens, and that's okay. But you'll need to specify in a lot of cases. Some software will choose it for you automatically. Others, you'll need to specify what they call a geographic transformation. It's basically, it's a model that helps it map those two datums to each other for the region of the world that you're working in. And if you choose the wrong one, you can end up with some substantial error. But usually if you choose the right one, your data aren't more than like a few meters off, which I know is like a deal breaker in some situations and totally acceptable in others. So some of them are even more accurate than that. I'm curious, Dennis, if you have anything to add to that, maybe.
Sorry, I was looking for my my mute button there.
Oh, no problem.
Yeah, I don't really have much to add to that. That's kind of the case there. It's just making sure that what I tell people is that one of the places that people get really screwed up on is when they're importing CSV files. And that's when you really have to choose the right projection or the coordinate system. So you actually have to ask who, produced that data and ask them, what is the geographic coordinate system? What is the projection used? Otherwise, you're going to be doing a scavenger hunt, essentially, which is not really a good thing to be doing.
Because like I had a problem where I have few shape files which are in a local coordinate system and I want to project it to a common coordinate system. So that's why I was like,
Yeah, so in that case, you want to do a transformation. Because the shapefile will typically already have the coordinate system that's using embedded in the file.
right.
And so that with that, you would assume that is accurate, and you don't have to overwrite it. So you would use a transformation to just convert it from the current one to the one that you actually need or want.
Okay.
Yeah, and I had in my head, I thought that I was pretty sure that there was a list of available transformations. So on epsg.io, if you're wondering about choosing the geographic transformation, if you need to change the underlying datum, if you look up the code or the name of your local coordinate system, so this is the local coordinate system I'm most frequently using. You could see available transformations to EPSG 4326. That's WGS 1984. That's a different datum than NAD 1983. So that's going to need to undergo that transformation process we're talking about in order to, that lossy transformation process in order to transform the coordinates. And they give you some available ones and tell you about potential accuracy for and what areas they should be used in. So if I have data that is in California south of latitude 36.5, I can get 2-meter accuracy using this transformation, and on depending upon your area. So some software will just use like one for the whole country, but if you have more local data than that, you can find a better transformation. And so, and these aren't just specific to this coordinate system. These transformations are really about this geographic coordinate system and datum, not this projected coordinate system on top.
Okay.
So hopefully that can help you find potential coordinate system transformations and accuracy information about them for your local coordinate system.
Yep, I think it will. Thank you.
Yeah, and also thanks for mentioning that about CSV files, Dennis. Now I'm wishing that I had done that, because a common task I usually do in an intro course is, people frequently get point data off of a GPS, or they get sent a CSV file from somebody that has a bunch of attributes and then a latitude and a longitude, and being able to transform that into spatially enabled information. It's spatial with the coordinates, but into data that you can run spatial operations on is helpful. But like you said, you need to know the coordinate system that the data came in, because sometimes it's latitude and longitude. Sometimes you just get a column that says northing and one that says easting, and units you can assume are in meters, but there are hundreds, probably thousands of projections with northings and eastings in meters, and you won't know anything about what it is until you talk to the person who created it. Trying to find it, as he said, that scavenger hunt without information from where you got it is it's something we've all done and don't want to do again if we can avoid it. So, but it's a useful skill to be able to take a CSV file and spatially enable it. Okay. Any other questions right now? Okay, we're gonna leave projections behind, but we will need to be aware of them in everything we do, including in this next step. And we're gonna enter the final part of this, which is going to very briefly introduce raster data and show how you would do, I think of it as the equivalent of a raster to vector spatial join. It's not a spatial join, but it kind of is. But I'll explain why it's not the same in a moment. As a reminder, Finder probably shut you down. You have your notebook open, but I no longer have a kernel. So if I click no kernel, click Python 3, IPyKernel, and select. We almost don't need anything from above this spot, but we do need the CV basins object. So you can either just run everything above this spot, or what you can do is it's for the best, because we want the version of CV basins that we finished with. So what I would recommend is click here, do run all above selected cell. If you want it to run faster, because I found it's a little slow in some things, you can comment out all the times it renders a web map and it'll speed up, but that's also some work. So I'm not gonna do that. I'm gonna tell it to run all above selected cell, and we'll talk about some other stuff while we get to being able to run this. Well, that was much faster than I expected. Okay. I'm assuming that went well for now. We're just gonna assume that went well. I must be running on a different server than I was running on yesterday, because yesterday they'd get like 5 steps in and then freeze up and I'd have to babysit it. So hopefully you're all running on the same one that I'm running on. But if yours isn't finished yet, that's okay. We're gonna talk about the code here. So we're importing some new libraries, one of which is Rasterio, raster.io, and then matplotlib, which you've probably seen if you've worked with Python in other places. Matplotlib gives us image-based charts or graphics, and then Rasterio reads and manipulates raster data. I think it might not even have a dependency on GDAL. I think that's one of its selling points, but I could have sworn that in the past I needed to install GDAL for it. Anyway, but when I was saying earlier that people recommend you don't use GDAL bindings directly in Python, they recommend you use something else. This is the something else to use. If you need to work with raster data in Python, Rasterio is a good package to do it with. So I'll mention that. The other thing I'll do as an aside is I'll say, so QGIS and ArcGIS, I have the icons down here. They're both excellent packages. QGIS is free and open source. ArcGIS is very proprietary. And they both have their advantages. ArcGIS's documentation is excellent. They also have excellent Python bindings with excellent documentation. So know that that's an alternative. And especially if you work at a university, you probably most likely you have a site license for ArcGIS in most cases, because Esri really wants universities to have site licenses, and makes them very, very affordable, so that they will. So you might check that if you want something, a very well documented API that provides some alternative functionality to the open source stuff. You can do everything you need with these open source packages. And I won't say like Esri is better or worse. It's just it's another option. So I wanted to mention that it has strong Python bindings that work with raster data, vector data. They can do everything we've done so far and a whole lot more as well. So that's all I'm going to say about that, though. But for now, for raster data, we're working with Raster.io, Rasterio. And it's actually pretty simple here, which is pretty cool. All we do is I have this path to an image, which we can see in this folder here. If it'll let me drag that. No, okay, here we go. We can see this image is right here in this data folder with the notebook. So that's just the path to that. We tell Rasterio to open it, and then we are reading it. And this is saying the first band of the image. Rasters can have many sets of values covering the same space, which we call bands. So read the first band and then apply this color map, because the data in the grid is just raw values. We're used to images that show color, but that's because we're applying color to values stored in a grid. So I just chose cool warm R. I'll note if I add some gibberish to here and run this, it'll give me an error. And if I scroll down, this is just the quick and wrong way to find out all of the color map values. I'm sure there's documentation somewhere on what these color map values are, but if you wanted to try out some other ones, here are some other options. And what this is doing is usually this is just applying a color for the lowest value and a color for the highest value and stretching all the other values in between. So for this raster, dark red is low, lighter values are higher. And the raster that I loaded up is, it's a grid of evapotranspiration information. That's the amount of water evaporating off the land and transpiring through plants into the atmosphere. I work a lot with it because we call it consumptive use of water. So you can think of it if water systems are locally closed, but there might be water flowing in from outside and leaving down a river, the other way water leaves is evapotranspiration. So it helps us fill out water balance models. And I've scaled this grid. So these are 1 kilometer pixels. Every pixel here has 1 kilometer to each side of it, which we would be able to see if we zoomed in. Notably, I'm plotting this in a different way than Folium, because getting raster data onto Folium maps is, it's not something I know how to do yet. So I tried a bunch of ways and I was like, I'm just going to plot it because this is really simple and you can see it pretty quickly. Yeah, that's a quick introduction to rasters. This probably looks pretty familiar in a lot of ways, and you can even see the familiar outlines of a lot of features in the landscape. But this isn't a terrain map. This is a map of water coming off the landscape. It just happens to mimic terrain in a lot of ways. Any thoughts, questions? Why are we doing this thing? Could I do X or Y instead? Anything? Okay. So you can do full analysis work all with raster data. You can overlay grids, but things you'd want to be aware of are those grids may not fully align, because at each projection and raster within a projection can start at a different origin point. Notice that it's plotting 0, 0 up here in the top left. And then basically a raster projection often, you know, it's north in the current projection is usually up in the raster. And that means that different projections that have slightly different alignments can cause rasters to skew one way or another. So even rasters with the same origin point, if they're in different projections, can kind of overlay each other like this instead of like this, which means that calculations between cells may not do always what you expect them to do. And especially on large scales, the cells may kind of change shape in some ways where they won't overlay as well. There won't be a one-to-one correspondence everywhere. So you got to be careful about that. And then, oh, there's something else I was going to say about that. Oh, rasters can have different cell sizes. So these ones, like I said, are 1 kilometer to a side of each pixel, but you might have ones that are smaller or larger. And if you're trying to overlay data, you need to have some way to get cells to match 1-to-1 so that you can do mathematical operations between them. So those are situations where you might want to resample a raster or regrid it so that you have grids that perfectly overlay and that you specified the trade-offs that went into recalculating the values of the cells before you start working with rasters together. Reasons you might want to do that and keep everything working with raster data, because you can convert vector data to raster data too. You could say, I've got these groundwater basins and they have, you know, at the end they have their areas, or they have some data that we're about to extract to them. You could assign every pixel within the groundwater basin the value, an attribute value. So you'd see kind of an outline of constant values for the groundwater basin here and here. That used to be really common in practice. The axiom was raster is faster, but vector is correcter. And those of you who work with, you know, meaning you can run raster calculations faster, but vector data is usually more precise. I think that falls apart a little, because even though computers are really great at, you know, raster data, you can do parallel computation. So most libraries are optimized for running, you know, numerous pixels at the same time and doing it super fast. But the data density that we've started to gain in raster data, there's so much there that oftentimes running an analysis fully with raster data is actually quite a bit slower these days. You know, it's kind of a privilege to have that much data and have it run slower. But you may want to take some steps if you're not running on a supercomputer or some kind of cluster to get out of raster and work with the data another way. So that's one of the things we're about to do here, which is convert raster data to attribute information on our polygons. So I know I just said a lot of stuff without a lot of visual aids. Did any of that make sense? Some of it, all of it, none of it? Okay. So let's do that. That thing that I said was basically a spatial join before. And looks like maybe it didn't run everything above. So I'm gonna click into my cell here. And let's do this. Kernel, restart kernel and run up to selected cell. And that way I'm just going to get everything into a consistent state. It clears all my outputs and I'll be able to see when everything's been run. So it's done some of this stuff already. Now it's loading the data again. So this will take time as it downloads data and processes it and starts displaying these maps, but we'll get caught up pretty quickly here. So let's talk a little bit about this. There's a package called rasterstat that lets us do, and the documentation for it's linked here. If we want to join raster data to vector data, there's not really, you can overlay it, but that part's not hard. But what information do you take from the raster data to the vector data is a not intuitive question, I guess. And the answer to that is usually what we call zonal statistics, where instead of trying to attribute some exact value from the raster to, let's say, a polygon, like our groundwater basins, you do some basic summary statistics of the cells, the values that are in the raster, in the locations that overlay each polygon, and then you add that information as new fields to your data table. Does that make sense? Any questions about that? We're about to do it, so some of those questions might get answered, but
I just had a question. So the raster data is point data, and then we have basically the vectors for like the basins now. And what we would want to do is some sort of an aggregation, you're trying to say, like from rasters to this basin data?
yeah, I wouldn't particularly describe rasters as point data, but it's reasonable to think of it conceptually like that. The difference I draw is that a point is, its location, and a raster value is meant to represent the area of the entire raster cell in the grid. People often think of point values as the point plus some vicinity, so it's reasonable, but I just want to draw that distinction that it's not officially point data. But the rest of it, yes, everything you said,
Okay.
that is what we're doing.
So like I'll consider the point to be the resolution of the raster. So if it's 4 kilometer by 4 kilometer, that's 1 point.
Yeah, and it's easy enough if you have a grid of regularly spaced points to make them into a raster, or make a raster into points by taking the cell centers or whatever that is. Yeah.
Okay. Mm-hmm.
Okay, and we're still waiting for this to catch up before we run anything, just checking on it. This is what I was talking about before. These renderings go pretty slow here. But it should. Let's see if I can get it to skip some of this stuff. Kernel's busy though. Okay, we're gonna let keep doing its thing, and we're gonna talk through some of what's happening down here. Okay, so I imported raster stats. I imported Fiona here, but we actually, I think I removed the part where we needed it. Raster stats is going to open all of our files for us, but Fiona is a package that reads and writes vector data. So I'm removing that index I added earlier, so that it can be more well behaved, and I'm writing the data out to a file. Mostly just to demonstrate raster stats and how simple it is, but also I don't think it accepts, it'll accept a Fiona file handle basically, but I don't think it'll accept a GeoPandas object. So we gotta get it into a format raster stats is ready for. And the way I'm doing that is I'm writing, so this is a way to save out a data frame that you could then send to someone else, or geodata frame is just geodata frame dot to file, and then the path. And in this case, I'm writing out a geo package. That's a more modern format for spatial data interchange. You've heard shapefiles used here. We downloaded some shapefiles. Those are super old. They have a lot of trade-offs associated with them. And so geo packages are meant to be kind of the open container that replaces the role that shapefiles have. So I'm saying write out to outputs.geopackage, which it'll create for us with the name CV basins inside that geopackage. And then I tell it that the driver it's using to write its geopackage. And the important thing I'll note here is geopackages, they're just SQLite databases with specific metadata tables and specific formats of data stored in them. So that's pretty cool. You can inspect them with anything that can read a SQLite database. You can also extract the data with anything that can read a SQLite database. So that makes them pretty handy. And, even aside from the fact that it's an open spec, there's a lot of tooling that's ready to work with them right off the bat, even if you're not working with spatial tooling. And then again, here I'm defining the path to that that ET raster. It's stored as a geotiff, similar to geopackages built on SQLite. Geotiffs are TIFF images, long time open specification for imagery, very flexible, and geotiffs provide an ability to reference them in space. If I want to run zonal statistics, get those stats, and for different groundwater basins, all I need to do is provide the path to the vector data, the path to the raster. When I provide the path to the vector data as a geopackage, though, I need to tell it what the layer name is that we wrote out inside the geopackage, and I tell it what statistics I want it to do. And so I'm going to tell it to do the min, the max, the mean, the standard deviation, and how many cells are within each polygon. How many cells of the raster are matched to the polygon with the count. And as long as this finishes running, which, yeah, this is what was happening to me before, is it just would stall out on one of these. So I'm gonna interrupt the kernel if I can. For some reason, like this works fine when running it regularly, but if I run it back to back with the rest of these, it's giving me grief. I also have this on my machine, but I kind of want to get it where you all can run it too, because I assume it's probably behaving pretty similarly for anyone else who's following along. Okay, what I'm going to do, I'm going to restart the kernel and be picky about what I run. Okay, so I'm going to run we're going to run this first cell, which is simple. And then I need to run, we can scroll down and run just the one that retrieves the groundwater basins. Just below this GeoPandas graphic. So that gets our original data as the basins file. We don't need to run any of the stuff that maps it. We then can skip over all of this. We do need to get the Central Valley boundary though. So we're going to run the cell just above the joining in space header here. Retrieve the Central Valley boundary. Oh, we got to run the one above it because I'm reprojecting. So run. Okay, well, apparently I need to run everything that creates anything, but we're going to skip the mapping cells. There we go. So run CV basins equals basins.loc here. Skip the mapping. I'm going to comment out the mapping on this one and run it. So comment out the last line and run it. And now I'm going to run the one that retrieves boundaries. Sorry, I'm just trying to do minimal required interventions here. And if anyone wants me to slow down and show anything else, again, I can. Okay, and then I don't think we need any of these or this. But we do want the results of this last section on spatial joins. So I'm going to run each of these in turn here. This is what we're actually going to need for our last section there. So we'll run all of them. I'll skip the final one that maps it, but other than that, all of them. Okay. So now, if I scroll down to here, I should be able to run this call to raster stats. It does give me one warning because I'm not specifying a parameter it would prefer. If I should specify no data equals whatever no data means. So rasters have null values that are just typically, like an integer that is set to the no data value. So raster stats says, I want you to tell me what value in the raster means the cell is actually null. And it defaults to -999. But then I'm printing just the first result from this, because what raster stats does is it gives me a list of these dictionaries with stats. With the statistics I requested, the minimum, the maximum, the mean, the count, and the standard deviation. So this is the result for a single groundwater basin. The minimum value of the cells that fall within it, the maximum value of the cells that fall within it, the mean, standard deviation, and that 304 raster cells fell within my polygon. The problem is, anyone see the problem right away without reading even further? Even if you don't say it out loud, if you think about it, but you can't say it out loud. The problem is I don't know which groundwater basin this is for, right? It's possible that these are coming out in the same order as they are stored in the geo package. And it's possible that the geo package has the same order that the GeoPandas data frame has, but I don't like to rely on that. And I think I searched at one point the raster stats documentation for confirmation that that's the behavior, and I don't think it was there. And so I don't want to rely on that. So that means that in practice, I don't really use this simple of a version of raster stats. I usually do something a little more like what we're going to do down below, so that I can actually get the basin identifier here along with the statistics. Does that make sense why this is limiting? Like, okay, this is data, but I don't know what the data corresponds to. Okay. And then I put a note at the top of this cell. This looks like a lot of code, but it's almost all comments. So yeah, there's a function with 3 lines and 3 other lines in a print statement here. So this is a big block, but it's really just that hopefully you could come back and reference all this. I'm trying to tell you more than just if you sat here and read it, but I tried to also provide a lot of context here for what's happening and why. So the big thing here is actually sort of hidden at the end, which is that raster stats, if I specify GeoJSON out equals true, and this is an implementation specific detail, other zonal stats things will provide you an identifier automatically, including in both QGIS and ArcGIS if you run them in the desktop. Raster stats doesn't, but if I specify GeoJSON out equals true, instead of returning just the stats, it'll give me a GeoJSON object of my polygon, including its entire geometry, which is, in some cases, a lot of data, as well as the statistics embedded with the attributes that are already in the record. So I get all the attributes of the record and all the attributes of statistics plus the geometry. That's great. I could just roll with that. But I don't like rolling with that because now I'm floating around a separate copy of the data that I either need to write out or extract from. So the paradigm I usually use is I have a function that subsets to just the parts I want to keep that I can then join back to my input data with just an attribute join later on. And that's what this function's for. So this is raster stats implementation detail that GeoJSON out will give me the original attributes along with the statistics, and this function helps filter it down so I don't have an unwieldy amount of data and gets me almost this data structure, but with my identifiers attached. So what it does that raster stats also has an optional prefix. So I put a prefix in front of the stats of just ET underscore. So these will become ET min, ET max, ET mean, and that way when I go join this data to something else, I'll know what min, max, and mean I'm talking about. So it'll give us that. So I provide that. And then what this does, this function, when I call it, I give it one record of GeoJSON. I tell it the stats that were available that I'm passing through raster stats. I give it the prefix value that's down here. And I tell it what attributes from the original object I want to keep. And this list comprehension merges the things I want to keep along with applying the prefix to the stats and keeping those. So then we have a list of field names that we are going to search for in the GeoJSON object that we want to keep. And then this dictionary comprehension makes the dictionary for the field names we want to keep, which includes the statistics and the identifiers. So I realize this is dense code. I'm like, it's only a few lines of code, but it's also pretty dense code. But what we do is we define our statistics, we run raster stats basically the same way as before. And then we iterate through the results in a list comprehension here, calling that function for every record that does the filtering and saying, I want you to keep the global identifier off of the groundwater basins and the basin name. These are data specific though. This is up to you. You specify whatever attributes are in your data. And then we can take a look at the results. So let's run that. So that's just one result. And we see now we have the values are prefixed with ET. And we also have those identifiers that came off of the data. So now we actually can say, oh, these values correspond to the record with this global ID and this basin name. We don't have to keep both, but I like having some other descriptive things so I can actually check and look at it myself instead of just being like, okay, here's the GUID. Cool. And now we can just use a standard tabular join to attach it back to our original data. Or we can just write it out to a CSV file or however we want to save it. So in this case, I just load it up into a data frame. So that's part of why I like keeping it as a dictionary, is I can either use the CSV package in Python or just make a pandas data frame and then dump it to a CSV like I am right here to save the results out. But now I can also see very easily in a Jupyter notebook, if it's a data frame, more than one record. Any questions so far? I realize I kind of breezed through some dense code here, but I'm hoping that these comments also help explain it.
I'll just mention that there's about 5 minutes left.
Okay, thank you.
Yes.
I haven't checking. I only have 2 more cells, but we'll move fast through those, leave time for any additional questions and wrap up.
Sounds great. Thank you.
So yeah, I won't draw on this since this isn't even spatial anymore. This is all just a tabular join. This is me taking these fields and attaching them back to our input data, our CV basins data that we had before, where we filtered to the Central Valley groundwater basins. And if I do that join and then take a look at it, I can see the input data, and it now has this ET data appended to the end. So I've joined summary statistics from the raster back to my input vector data here. And somewhere in the middle here, there should be a geometry field. Yeah, because here's our basins. It's probably right here. And now if I use the explore tool for GeoPandas, since this is a GeoPandas data frame still, I just did a standard tabular join onto it. Explore will plot me a map and I'll see all these attributes, including my ET per polygon. So while it's rendering, cool. So now I can hover over and see all the attributes of any polygon here, including all the ET data we just extracted from the raster to the polygons. Any questions about that? That was fast for the raster data, I know. Okay, well, in terms of wrap up, the repository location, yeah, that's gonna still be there. And so that's here, I'll pop it back in the chat. You can feel free to clone the repository to your own GitHub, download the notebook, whatever you like. If you would like to keep a copy of this. Like I said earlier, pull requests are welcome if you have things that you think would make it clearer. I plan to add a little bit more stuff to this that would help clarify some of the pain points. And then, like I said before too, this is designed so that it could be gone through not instructor led. There, tons of comments here to try to explain things. So feel free if you want to pass along to colleagues. And then there's some stuff at the bottom here about data formats that I was going to get to if I had time, but I wanted written down. And then link to package documentation, a few other resources that teach spatial data, and then some information on getting spatial data stacks for Python installed on your own machines. So if you're like, okay, I've done in the notebook, but I want to get running in Python on my computer, here's some information on getting started there. So I think that's it. I'm happy to answer questions. I'm happy to stick around. Thank you all for sticking through this. I know it was a lot of me talking at you.
Awesome. Thank you so much, Nick. It was excellent. I'd like to remind everyone that the recording and the Jupyter Notebook will be available. Again, if you're not a member of US-RSE and would like to become one, we do have this link here in the chat. And we do also have a feedback form for the tutorial sessions in general. So that is here. I'm going to send it in an email after the fact as well, but that will help inform us how we might do conferences and tutorials for the conference in the future. So your feedback is very helpful. I think we have 1 minute for questions, and then if Nick wants to stay on, you're more than welcome. Nobody here should feel obligated to stay. Yes, lots of thank yous in the chat.
You're very welcome. I hope it's useful. I'd be curious if any of you know what you want to use it for, or if you're just learning today.
Hi, Nick. This is Mark.
Hi, Mark.
Hi. Thank you so much. This was very useful. I have a question about polygons. So I've used Google Maps. I've used Google Maps API before, and I'm really this is great because I'm really glad to learn Python, so I have an alternative to the Google Maps. I was wondering if you knew about. So I'm trying to figure out how to explain it. I had a problem where I was working with zip codes, and some zip codes are polygons that are like two areas that are completely disconnected, but they're in the same zip code, for example, and those do exist. And I really tried to create like a single polygon that represented two areas that were disconnected. Is that something that we can't do, or that I couldn't get it? I couldn't do it in Google Maps. Have you ever like seen anything like this? Do you know how to do that, or is that just a limitation of polygons?
That's probably a limitation of their implementation. What we would commonly call something like that, at least Esri's terminology for this, but I don't think it's implementation specific, is a multi-part polygon. Okay. And that dissolve functionality I showed you earlier where we did the aggregation, that's one way to basically get a multi-part polygon in a lot of tools. I don't know if dissolve on GeoPandas will produce multi-part polygons. Not everything supports them. But basically you've got multiple geometries associated with a single attribute record, treat the whole thing as one. So lots of spatial data formats for storage do support multi-part polygons though. But I don't know what, again, multi-part polygons being, you have multiple disconnected pieces that should all be treated as one unit. You don't need to necessarily have some connecting spatial data between them to make them all, officially one long line going around everything or something. So, but in a lot of systems, the way you would get that is by dissolving on some attribute that defines it. So in your case, if you dissolve on the zip code value, your results would produce a multi-part polygon. You just need to be careful with that, because if you have multiple records for zip codes or something before that have distinct attributes, you're going to lose all those attributes when you dissolve. And so when you dissolve to create the multi-part, you'll then want to join your existing attributes back to your new dissolved data with the multi-part polygons. Does that make any sense?
Mhm. Thank you. Mhm. You said aggregation?
Yeah, the section where we did aggregation after the spatial join, there was a
Okay.
call to geopandas.dissolve or is a data frame .dissolve. And that operation, that's probably coming from Shapely. So the Shapely library, if you're not using a GeoPandas data frame, but you want to operate just directly on some spatial data, you should be able to do a dissolve with Shapely, which might help indicate which formats support it. And then, I mean, GeoJSON in general, I think should, like, let's say you didn't want to do it on Google Maps. If you wanted an alternative, you could do a leaflet map, which is just a really simple web map. That's what Folium is embedding, is a leaflet map, but it's very conceptually simple, easy to code. And if you were to convert your data to GeoJSON, GeoJSON supports multiple geometries per attribute record, just because it's a pretty flexible format. So you should be able to do multiple polygons with one set of attributes and embed it on a leaflet map. Does that answer your question
Yes.
enough?
But,
Okay.
Yeah, that's great. Thank you.
Mhm.
Any other questions?
So you ran your Jupyter notebook on Binder. Um, d- um, do we get a copy of that notebook, or is it in GitHub? Can we run it locally, or does it just run on Binder?
Yeah, if you the link I just put in the chat, you can clone that whole repository if you want a copy of it. It'll run locally. There's a Conda environment file there that you can use. Notably, I'm not running it in Conda on my computer. I installed the dependencies using the method linked at the very bottom of the notebook for installing on Windows. Because I'll preface this, running GeoPandas on Windows has been a total pain in my butt, to the point that I basically didn't do it for a long time until I recently figured out a way to do it without needing to build a Conda environment. That's all described at the bottom there in that Windows section. But on other platforms, it's not as bad. On Linux in particular, it works pretty well. And on Windows, if you get it right, it's fine to install. So, but yeah, I developed this all locally. I ran the notebook locally. I just deployed to Binder for this workshop, or deployed to GitHub to deploy to Binder.
Okay, great. So unless there's any more questions, I think we can finish up and head out. So I'll stay for a bit, but everyone feel free.
I just had one thing I wanted to ask. I am working with some of the spatial data where we have like netcdf files which have like point data for some years, and I'm trying to map it to a grid selection that's there on the ground. But the whole thing takes too much time. But I mean, I'm just trying to learn like how would you do the point selection, and based on that, like, is there any resource which I can refer to, like maybe a book or like articles somewhere?
On point selection for net CDF files, or sorry, could you elaborate a little on that?
So what I'm trying to do is like I like literally do not know what it's being used for. So what I know is like the buzzwords. They are like, it's like the forcing data is something that I'm trying to create. So we have a netcdf file which has like data from like a few years, and it is, I think, hourly. And there is a grid selection which I'm trying to map it to. So I'm just selecting the closest point to the grid that I have in the netcdf and then aggregating a bunch of variables.
Okay. And what's your question about that? So just like
So
any information on how to go about that?
yes, so I'm looking for like, if you know what I'm trying to do is I'm just trying to find some things on like Stack Overflow and stuff, like how to approach it. But now that I see like there are a lot of caveats when we have such conversions, so it could be like lossy, but from my understanding. So
Yeah, and so I'll say like I have worked with netcdf files. I don't like it. They're important, they're valuable. I have a link in the bottom of the tutorial to a format that's kind of aiming to replace them for multi-dimensional data in the cloud. And I'm kind of looking forward to that. But so I guess that's all by way of saying I might not be the best person to answer that, because I don't know the good tools for netcdf files. There's a who is it?
Xarray is usually what people use in Python.
Yeah, thank
yeah.
you.
Yeah.
And then who is it that they produce all kinds of netcdf files? They maintain a page of like tooling that people have used.
I know what you're talking about.
It's
Hold on.
oh, I have it in my other browser profile. It's Unidata. Unidata, the organization that UCAR's Unidata, they have a page on all kinds of tools, anything people have like ever built that works on netcdf files, I feel like is on this page.
Mhm.
And so, Lauren, it sounds like maybe you are a better person to answer this question than I would be. I'll be quiet if you or Dennis or anyone else has thoughts on this.
Yeah, Dennis might know more. I've worked with oceanography data. And basically whenever I had to change, like go from something that's like a grid to something that's more flat, I was given basically the matrix to do the multiplications and stuff. Remember that part was, if I did anything special to speed that up, I don't know. Like you can yeah, I'm not too sure. So I think are the files big? Are there a lot of files?
So I think I have to experiment with them a lot.
Yeah.
And that's sort of getting a little bit like, so like I'm resampling like for different times, interpolating, probably extrapolating, and something like that, just to see if we can have a good sort of modeling based off of that forcing.
Yeah. Like Dennis might have something. He's done this more recently.
Yeah, I'd say like the best performing tool is I find is GDAL, the command line. That thing has many ways of transforming data from one file format to another, and you can specify grids and sizes and all kinds of things, and it doesn't overwhelm the memory of the machine because it kind of does in series and in chunks. Once you get into Python and R or tools, it tends to blow up the memory footprint and can really slow things down. But that is more of an advanced way of doing things, and the documentation is not as clear cut as tools for Python or R. Xarray might be another tool that is purposely made for NetCDF, as far as I can tell. And they might have some good resampling tools there, but I'm not too familiar with them just yet. So
Yeah, like I'm using Xarray for like the data fetching and like the things, because it's sort of like it makes it parallel, but I think my forcing still takes like an hour long or 2 hours.
yeah. So another thing you can look into is Dask is sort of built on top of NumPy, and it kind of feeds with Xarray, and so that's sort of a parallelized approach. And so if you have a system, if you have access to a system that is multi-core, 16 cores, 32 cores, and you choose appropriate chunking size, then you can have each of those workers actually work on a chunk, and that can often speed up the process. But with Dask, with spatial data and Dask, you can create really complex graphs, which the graphs are kind of the individual steps that Dask is going to need to take to get from the starting point to the ending point for your analysis. And those can get really complex and can also consume a lot of memory. And so that you kind of have to play around with it and try to minimize that graph as much as you can to really extract optimization of that process. So again, those are additional tools. There's plenty of tools out there that's going to try to help you make things work faster and deal with big data, but they do have the upfront costs of learning them and trying to figure them out.
Okay, thank you so much. I think I'll give it a try, which has like a smaller learning curve, which
Yeah,
probably none would have.
I agree with everything they said. Before I started working with Xarray, I would slice out parts of NetCDF files with GDAL. And I think what Dennis said, like if you have slow, large data that's taking a long time to work with in Xarray and you want to chunk it, I mean, if it loads up, you could chunk it with Xarray, but if not, you could slice it up with GDAL and then work on the subsets of it. So I like that suggestion.